Hello, this is Flava MCP Hubs. I will now begin the presentation. The presentation will be given by the two of us. First, if I may start, hello. From 2018, Line Plus created the in-house cloud Verta and the next generation platform Flava. I am Park Min Hyuk, currently the tech lead for the Flava MC Fair division. Hello, I am Inbei Kang, and I have been developing Verta and Flava in the same team since 2020. Currently, I am in charge of the backend for Flava MCP Pure B. First, I'd like to tell you what topics we'll be covering today. Today's presentation is divided into 5 main chapters. First, I will explain why we had no choice but to create MCP Hub and what kind of platform it is. Secondly, I will explain the structure we call the 4-layer backbone model, which is how the MCP hub actually operates internally. Third, I'd like to share how we bridge the protocol gap between standards and in-house authentication, which was one of the most challenging aspects among the 4 layers. Fourth, we initially used an open source gateway, but ultimately, this is a story about the process that led us to decide to build it ourselves. Lastly, we will share what has only become visible since this became a single platform, and the path that still lies ahead. Then, let's dive right into the first chapter. First, let's look at what Flava MCP Hub is and why we created it. MCP stands for Model Context Protocol. Then, what is Model Context Protocol? LLM is smart, but at the point where the learning is finished, my mind is blank. What is happening in our system right now? LLMs do not know what data has been accumulated. You have a good mind. This means we have no eyes to see what's happening outside, nor hands to act. MCP server is a standard that gives eyes and hands to LLM. LLM can directly access external tools and data, so it serves the role of allowing us to retrieve necessary context as needed. Now, we've briefly learned about MCP. Let's return to the main topic and talk about what the Flavors MCP Hub is. Flava is a private cloud commonly used within the company. And the MCP platform commonly used in the Warriors that went on top of Flava is the Flava MCP Hub. The identity of the Flavor MCP Hub can be expressed in 3 words: catalog, runtime, and Earth Gateway. First, the catalog serves to provide an at-a-glance view of what MCP servers are available internally. It eliminates the question of what MCP server can be used internally. The runtime makes it easy to create, deploy, and use MCP server directly. And finally, the Earth Gateway acts as an authentication gateway that allows for easy setup of permissions and access control. The Flava MCP server simultaneously takes on these 3 roles. So now internally, in actuality, let's take a look at how much it's being used. Let's look at the numbers MCP Hub has accumulated since the service launch. There are over 650 MCP servers running, more than 200 teams are using it, and the cumulative number of tool calls has exceeded 11.5 million. In fact, it quickly became the standard infrastructure within the company. However, I think you might not grasp the full scope of these numbers since they are just numbers. I have prepared a short demo. We have prepared 2 demos. The first is Flavor MCP Hub. Among various MCP servers, there is also Confluence MCP. Let's take a look at the TechVerse 2026 schedule using Confluence MCP. Secondly, we directly created a Kubernetes MCP server. I will demonstrate how to look up workloads in a specific namespace. What's surprising is that each of these two things takes only 1 minute. First, let's watch the demo video. We will now take a look. Hong Kong. Just a moment. The screen you are currently seeing is the Flava console. Let's now go into the MCP app. Then you will see a list of MCPs that can be used on this initial screen. And I will go into Confluence MCP. As you can see, there is a one-click install button. If you click this, VS Code will automatically launch, and the MCP server settings screen will immediately appear. If you press the install button here, the setup is immediately complete. About 15 seconds have passed. We were able to configure it quickly. I'd like to ask about the Tech Week schedule. Then, using the Confluence tool, LLM will generate an answer. Oh, the answer came right away. We provide MCP server in such a way that it can be used easily and conveniently in a short amount of time. And the second demo, as I mentioned earlier, is to create a Kubernetes MCP and then query the workload of a specific namespace. Let's take a look. This is Bingbingbo Abushiz. This is the screen you saw earlier. I will create a Kubernetes MCP using a predefined template. Here, you enter the name. And since it is Kubernetes MCP, I will create an MCP server using the pre-prepared kubeconfig. Please wait a moment, and the MCP server will become active. This time, we also provide a playground environment where you can easily test, and you can try using MCP there. I will ask. We set up the MCP that we just created. I will ask to retrieve the cron jobs in a specific namespace. If you ask this way, you can see the LLM generate a response using the resource list tool itself. We provide a simple and convenient way to not only use MCP, but also to create, deploy, and finally use it. Let's now move on to how this easy-to-use platform actually works internally. However, before I show you the structure, I think it would be helpful for your understanding if we first go over the problem we initially had to solve. There were 4 issues we encountered while using MCP server internally. First, MCP server spread everywhere without control. Since each team created and used their own, no one knew what was running where. Secondly, the authentication methods were all different. Although MCP is powerful in context propagation, without proper access control, it can be a double-edged sword. However, having each team write authentication-related code directly was too costly. Thirdly, the in-house authentication could not keep up with the MCP server standard. We will discuss this in more detail in the protocol gap section later. Fourth, there was a complete lack of visibility. There was no data on who was using what or how much, so no one could make a judgment. To solve these 4 issues at once, we needed a common platform. So what we created is the Flava MCP Hub. We solved these issues using a 4-layer plumbing model. As the name suggests, it is structured with layers like pipes through which requests flow. Shall we trace a user's request once? As shown in the diagram, it starts from the client, passes through the connector and gateway, and reaches the MCP server at the very end. We have divided the responsibilities required for this flow into 4 layers. From the first floor connection, second floor proxy, third floor authorization to the fourth floor monitoring. Then, let's go up from the first floor in order. It is the first floor connection, where users first arrive. From the client's perspective, it's simply a matter of connecting using standard I/O. The connection is completed in a single line. However, the connector in the back, we are tackling a lot of complex tasks. The YDC flow token cache. When the token expires, it is automatically renewed, and the bearer header is also injected. It handles everything required for internal authentication. Thanks to this, the client is not even aware that they are attached to internal authentication. They just feel like they're connected to a normal MCP server. How this is possible will be explained in more detail in the protocol gap section later. I will explain it. Up. Moving up one level, we have the L2 proxy. Before the request received by the connector actually reaches the MCP server, this is where the policy is refined and determined for delivery. The core component is the MCP gateway. When the team deploys an MCP server, the gateway comes up with it, right in front of the server. Then, for authentication, course, header transformation, and transmission protocol, the gateway standardizes and processes all of these under the same protocol. Therefore, each team can focus solely on the MCP server logic without having to deal with anything else. Previously, each team implemented this differently, but now all duplication is eliminated as it's absorbed into the single layer of the gateway. So, how is authentication handled in this gateway? The answer is the third layer, authorization. When the gateway receives a request, the first thing it does is token validation. The token has already been issued by the connector on the first floor. Gateway receives a token and verifies various in-house authentication methods in one place. Previously, we had to write separate authentication codes for each MCP server. However, now that the gateway only passes validated requests, the server does not need to worry about authentication at all. The fourth and final layer is the monitoring layer, which supervises the three preceding layers. From the client to the MCP server, we collect all tool calls, authentication results, and latency throughout the entire section into a single pipeline. Now you can see at a glance who called it, when, and with what tool. Until the arrival of the Flavor MCP hub, internal MCP usage was completely invisible. As I mentioned earlier as a problem point, thanks to this impersonation, data began to accumulate for the first time, and it is now being used as input for our next design. We have thus reviewed the four-layer structure. Now, we'll delve a little deeper into one of the most challenging aspects, the gap between standards and internal authentication, which is the protocol gap. From here, Minyuk will continue the presentation. Thank you. When a user connects to the MCP server under the Flower MCP, they simply use their client. This was possible because we bridged this protocol gap internally. The gap between MCP server standards and in-house authentication. I will now show you how we connected the gaps. If you look at the screen, the left side is the MCP specification. To the right is our in-house authentication system. First, the MCP server standard on the left should be able to connect directly to the server that the client first encounters. Therefore, dynamic client registration like DCR and CIMD is a prerequisite. However, the internal authentication system on the right does not support such a standard. It is IM-based internally, and clients must be pre-registered, and tokens must also be obtained from the internal authentication system. In short, it's a structure that does not accept new clients. Therefore, there were two possible outcomes. If we follow the MCP standard as is, Our internal authentication system will not be supported. If we create it to fit the internal authentication system, then it won't be compatible with the MCP server standard. This area, which cannot be aligned with either side of this dashed box in the middle, is precisely the protocol gap we encountered. So, this gap actually completely separates the client and the MCP server. If there were no MCP server hub, each team would have had to memorize these broken sections on their own. Each team separately implements MCP server authentication and creates browser callbacks, catching, and refreshing tokens. The same set of authentication codes. Each team had to rewrite it. There. Not only that, but each team also had to bear the operational responsibility for the code they developed. Ultimately, the same problems recur in each team within the company. This is not a problem for individual teams to solve, but rather, this was a problem that the platform had to solve at once. The solution we chose is actually surprisingly simple. It is like adding another layer between two disconnected worlds. One layer is the connector. It's the purple box in the middle of the screen. From the client's perspective, the connector simply appears to be a standard STD-IOMCP server. Whether it's Codex, Claude Code, or Cursor, they will connect to the STIO-MCP standard as they know it. However, internally, the connector takes on all the complex tasks of internal authentication. From internal OIDC browser, callback token cache auto-renewal, to bearer header injection. This one layer absorbs all the complexity required for authentication. So, by the time the request exits to the right of the connector, it has already been authenticated. It will flow towards the MCP server. This one line at the bottom of the slide best illustrates the core idea. The client is unaware of the existence of internal authentication. This is how the connector bridges the protocol gap. As a result, the complexity on the client side was completely eliminated. Each team no longer needs to worry about authentication, right? So the numbers change like this. In the past, to obtain MCP certification, each team had to understand the internal certification process. To apply authentication, it was necessary to design the authentication system. If these processes are carried out, it is expected to take about a week. However, now that the connector handles everything, the team only needs to focus on the MCP server logic. The rest will be handled by the Flava MCP hub. This kind of task would be completed in 5 minutes. This 5-minute difference in 1 week is what a single layer of connection has created. This bridges the gap between MCP standards and industry certifications. After the release of the MCP Server Hub, we faced another problem. We were using an open source gateway, but we faced limitations and consequently decided to switch to a gateway we developed ourselves. I will explain why we independently developed it during this process and what we were able to learn from it. Initially, to quickly configure the gateway for Flava MCP Hub, we began by directly using open source projects. At the time, the development period given was limited to about 2 months, so realistically, it would have been too burdensome to implement all the gateway functions from scratch. Therefore, we utilized an already verified open source gateway. We were able to quickly secure the basic functions and structure. Through this, we avoid re-implementing common problems that have already been solved. The requirements needed for the line channel platform. We were able to focus more on the integration. However, we encountered several limitations while directly using open source gateways. The first was the difference in language stacks. Our team had many members familiar with Go, but that open source project was Rust based. It was difficult to analyze or debug failures. The second is the direction of open source and that internal requirements were not always correct. The open source's own goals and because there is a roadmap. It was difficult to reflect the necessary technologies or requirements at the desired speed. Third, there was the burden of managing forks and patches to handle necessary changes in the internal authentication system as upstream issues or PRs. We had to manage it as a separate fork. In this process, I will introduce a few issues where it was difficult to use the basic open source software as is. The first was a JWS compatibility issue. Within the JWS key provided by the in-house authentication system, it contained a key that uses the ES512 algorithm, but the framework we were using at the time could not parse this value. Even if you don't use keys for the actual specific financial transaction verification, failed during the JW case loading stage. There was an issue where the gateway was not operating. The second issue was the execution order between course and the authentication middleware. If the authentication middleware operates before CORS and authentication is enabled, the browser's pre-flight request was rejected before receiving the CORS header, so it did not function correctly. The third issue was memory stability. During the process of handling MCP server traffic, the gateway frequently encountered OOM errors. This made it difficult to predict the operational stability of the MCP server. As these problems accumulated, we determined that we needed our own gateway that could quickly fix necessary functions and control them according to the operating environment. During the redevelopment process, we proceeded in a direction that would allow us to improve existing issues. First, we redesigned the gateway to meet internal requirements. We implemented it to allow direct control over the core operations of the gateway. Also, as we re-implemented it based on, it has become easier to analyze failures and debug using familiar languages and tools within the team. And as we no longer depended on upstream or forks, we are shortening the patch cycle and we were able to quickly implement necessary feature improvements. Finally, based on these changes, operational stability and convenience have been improved. The lesson we learned from this experience is that while open source is a good choice for a quick start, it may not always be the right choice for our specific situation. Initially, we were able to reduce development time and quickly validate features by utilizing open source solutions. However, the goals that open source projects aim for. If the requirements for our operating environment keep changing, simply following along with forks or patches could increase the operational burden. In particular, with the recent ability to analyze and improve code using LLMs, the burden of direct development or migration has been significantly reduced compared to before. So rather than unconditionally replacing open source, we consider the direction of open source and we believe that developing our own solutions in areas where our requirements are not met can be a choice that enhances long-term stability. Ultimately, what is important is not the open source itself. Could we directly adopt a foundation that meets our operational requirements? Now, I will discuss what we actually observed after implementing the piping in the MCP Server Hub. First, the value we expected was platform efficiency. If each team starts creating their own MCP server, connection methods, authentication processes, authorization management, and operational approaches would have to be repeatedly implemented by each team. The MCP server was created to handle this repetitive task on the platform. teams no longer need to recreate the same integration pattern every time. Internal authentication and access control can also be used in a common way. Additionally, operational elements such as the server's visibility ownership policy can be consistently managed. As a result, the MCP hub creates a new server to cover the operating costs. TIC costs. It served as a pipeline that enabled teams to adopt MCP server more easily. However, once we laid the groundwork and started operating, unexpected value began to emerge. As multiple MCP servers were connected through the MCP hub, all tool calls naturally passed through the hub. We can also see which tools are actually used frequently and which team's MCP server was reused by other teams. This data goes beyond simple monitoring. It became the basis for platform decision making. For example, which features should be officially supported first? Which MCP server templates should be created? We can determine which features are important to actual users through traffic analysis. This means that initially, plumbing was installed to facilitate connections. After operations, the pipeline became an observation point for understanding the use of company-wide AI tools. The future direction is to further automate the remaining repetitive tasks in the process of introducing MCP server. The first is OpenAPI to MCP. Based on the OpenAPI specification, the direction is to enable exposing existing APIs to the MCP server. The second is internal Earth, API authentication that was previously implemented by each team. It is a feature that allows it to be used as is. The third is support for the latest MCP server specifications. As MCP server is a developing protocol, changes are frequent. Since the July 28th, 2026 version will be released soon, related changes will be implemented. Fourth is CLI and skills. Developers' actual CLI environment, or we plan to expand it so that it can be naturally used within the skill flow. The last one is IDJAG. This is aimed at automating token exchange and authority delegation between various systems to provide more secure and convenient cross-system access. Ultimately, the goal is to enable more teams to create, connect, and reuse MCPs. The platform takes on more of the burden of authentication and operation. I will elaborate on two related points. The first feature I would like to explain in more detail is OpenAPI to MCP. Many teams already have REST APIs. However, for an AI agent to use this API, currently, we implement a separate MCP server directly, or we need to implement the tool. OpenAPI to MCP to address these issues. The goal is to streamline the process. It transforms the API paths and operations into an MCP tool based on the open API specifications of the REST API that each team possesses. This means exposing it as an MCP server endpoint. This means that existing REST APIs do not need to be re-implemented as MCP server. Our goal is to provide it like an MCP server that agents can use. Next is IJAG. The direction of IJAG is this involves automating token exchange and delegated authorization within the platform. To use an existing MCP server, you must agree on the consent screen to grant the necessary permissions for each MCP server. We had to issue and use separate tokens for each MCP server. However, after IDJAG was introduced, you would be issued an IDJAG token. With this single token, you can exchange it for the necessary tokens at each MCP server and use it. Through this improvement, We no longer need to register and get consent for each MCP server or client as we did before. By exchanging tokens from the MCP server, they become interchangeable, which significantly increases usability. Thank you for listening to our presentation. Additional questions or discussions can be pursued at the Ask the Speaker session, so please feel free to attend. Thank you. Hello. I will begin my presentation on the compounding effect of good design experienced during the evolution of Line API Gateway. Before we begin, allow me to briefly introduce the presenters. I am Kim Giwon from the Line Channel Platform team. I joined Line Plus in 2020 and have been working on Line Channel Platform ever since. More recently, I have been primarily focused on developing the Moon framework, which I will discuss later.
I am Yajin Shin from the Line Channel Platform team. I joined Line Plus in 2018 and have been working with the Line Channel Platform team since 2019. The presentation order is as follows. First, we will introduce what kind of system Line Channel Platform is, and then we will look at the problems we have encountered. Next, I will explain the core strategies for solving these problems, and finally discuss what changes and achievements resulted from them. Let me define Line Channel Platform in one sentence. It is a single entry point that allows external and internal services to safely use Line's features. We are abstracting various Line functions into REST APIs and applying authentication and authorization to allow access only to authorized services. Line is a large-scale service used by 100 million people daily. The servers that support the work are divided into numerous components. If each component were to implement authentication and authorization separately, it would be difficult to maintain consistency, and the maintenance costs would become very high. Therefore, we manage common functions such as authentication, authorization, and traffic control by centralizing them in one place, serving as Line's API gateway. Line Channel Platform has been developed alongside Line and has now reached 15 years old. Over the course of 15 years, features have been continuously added, and we now offer over 700 APIs. In addition, the number of services using this API has now exceeded 14 million. As a result, we have become a platform of a scale that is not easily found. 30 billion. This is a number that is difficult to imagine. This is the number of requests that Line Channel Platform processes in a single day. There's a saying, competing with scale, isn't there? When the scale changes, the rules that apply also change. I believe software engineering is similar. There are things that work so naturally when they are small. However, as the scale grows, that certainty inevitably begins to break down. Today, we will discuss the problems we encountered, broadly divided into two categories: performance issues and interpersonal issues. The first issue I would like to discuss is performance and stability. The Line Channel platform was deployed on Tomcat using Spring Web. Tomcat is a typical synchronous model. To process one request, one thread is needed. We cannot endlessly increase threads, so we operate with a maximum number defined. Normally, there were no issues. However, if one upstream starts to slow down, the situation changes. Requests occupy threads for a longer time, and most threads end up waiting for slow upstream services. The server becomes unable to process even valid new requests. This phenomenon, known as thread busy, was one of the most frequent causes of outages on the 10up platform. Furthermore, Line Channel Platform is Line's centralized API gateway. Conversely, it was also a single point of failure. The Tenor platform receives requests from multiple clients and then forwards them to multiple upstreams. So if one upstream was slow, the entire system would often be affected. It was a typical chain failure. We reduced the frequency significantly by applying circuit breakers to each upstream, but it was not a fundamental solution. This problem did not arise due to a deficiency in Spring Web or Tomcat. The characteristics of our system, and the characteristics of the underlying tech stack were not a good match. Let's move on to the next issue, which is a problem between people. The Tina platform directly implemented in code how it would receive requests, what responses it would return, and how it would communicate with backend services. In fact, it was closer to the task of wrapping existing service APIs once more to provide them as new channel APIs. Over the past 15 years, numerous developers have created and maintained the Line Channel platform. As a result, different standards and methods began to accumulate. And at some point, Line Channel Platform became a somewhat dual component, being both a platform and a service. However, the problem did not end there. Our team itself became a bottleneck. Adding a channel API ultimately meant implementing new code on the Line Channel platform. Therefore, it was not something anyone could easily do, and even for the simplest API, it had to go through our team to be added. Although requests continued to pour in, there were limitations in the personnel and time available to process them. So, what did this bottleneck actually look like in practice? Let's recall a day in the past. You receive a Slack message. Hello, could you please add just one more API? As we proceeded with the project, we found that we needed one API. Yes, it usually starts like this. However, since this API has some business rules, I will also share the domain specifications. To properly understand the rules, this discussion ultimately arises. Could we arrange a meeting? Why was that the case? This is because to properly implement an API, one needs to understand the system and data at a level close to that of the person who created the API. In fact, we didn't even create the feature. As a result, a single API would require several meetings, and in severe cases, multiple people would work together to develop it. Understanding the specifications is not the end. We implement the code, write tests, verify them locally, and then submit a PR. Next, we receive team member reviews and create documentation. Only then can the API be used and released. In some cases, it took several weeks for production deployment. Additionally, documents were manually created on the wiki. As a result, the format would vary from author to author, and there were often cases where code changes were not reflected in the documentation. As these small collisions occurred, the reliability of the documentation gradually decreased. Once development is complete and deployed to production, it enters the operational phase. The Line Channel platform has a dedicated platform operations team. The operations team helps clients determine if they can use the API and assists them in doing so. To perform these tasks, it is, of course, essential to have a good understanding of APIs. The operations team primarily understood and operated the API based on documentation. So, you were looking at a different source of truth than the development team. Even when discussing the same API, there were instances where the understanding differed. The operations team is in charge of the API. There were instances where we had to call in both the service development team and the Line Channel platform development team to verify inquiries. The problems we have seen so far were largely twofold. One was a problem of performance and stability, and the other was a problem between people. Although they seemed like different problems, we decided not to solve them separately. Instead, we made a single decision. The biggest goal we set was selection and concentration. It was about clearly separating what we didn't have to do from what only we could do. We decided to focus on improving the gateway platform itself, leaving the design and implementation of APIs to the service providers who best understand the domain. This means minimizing the burden on the team when adding new APIs. However, we couldn't start this right away. The Line Channel platform is a large-scale platform consisting of over 300,000 lines of code. It was not realistic for service providers to directly write code here. So, what should we do? We have unleashed a powerful weapon that has been used in software engineering for a long time. It is abstraction. Actually, the essence of what an API gateway does is quite simple. It receives a request that has come in through a specific path and forwards it to a specific backend service. The rest of it is structured to add features such as authentication or rate limiting. These additional features can increase indefinitely, but the core remains unchanged. Ultimately, we believed that this core could be expressed in a structured format. This is the specification. The specification can be expressed in various ways. Code is also one way to express a specification. However, since implementation details are included, it can be expressed in different ways by different people, and room for interpretation can arise. However, we couldn't use natural language either. Therefore, we chose YAML. It was important that YAML was not difficult for humans to read, and especially that it had a good structure for machines to read. For example, you can read YAML to generate HTML documents, or convert them to Markdown to input them as prompts into LLMs. This means that one specification can be utilized in various ways. The specification itself becomes the single source of truth. Since we decided to prioritize specifications over code, we now needed a tool to properly handle those specifications. We looked at other API gateways, but we couldn't find a silver bullet that met all of our requirements. What we truly wanted to create at the time was not an API gateway itself. We wanted a system where the channel platform team would no longer be a bottleneck. So, in the end, we developed it ourselves. It is an API gateway framework based on the declarative specification called Moon. While we were developing the framework, we also redesigned our working methods together. From now on, I will walk you through what components the UI consists of and how the specification actually becomes an API gateway. Moon is built upon 4 pillars. First, its declarativeness. We express the behavior of the API gateway not in code but in YAML specifications. Second is dynamic reconfiguration. We can change the behavior without restarting the server. This feature has brought us great convenience in the operational process. Third is scalability. The core function of the API gateway is simple, but the features built on top of it have different requirements for each service. Therefore, we designed it so that necessary features can be added directly at any time. Fourth, it is high performance. It operates based on Armaria, an open-source asynchronous framework developed by Line. Thanks to this, we were able to reduce the problem of slow upstream holding threads for a long time and lower the risk of cascading failures. Before I explain the components of Moon, I would like to show you the specifications that are actually in use. This specification is a setting that transmits requests received via API to Line Dummy. The most basic operations of an API gateway are expressed in a few lines of YAML. In the past, we would have had to create a controller and service layer, and even implement an HTTP client to communicate with the backend. Now, a few lines of this YAML replace that role. In reality, an API gateway does not simply forward requests. Moon provides features like logging and authentication in the form of plugins. As you can see on the slide, the logging plugin has been added to the plugins. If you add this plugin, all requests and responses passing through this router will be logged. In this way, with Moon, you can combine necessary functions using just a few lines of YAML to configure a single API gateway. We have looked at what the YAML specification looks like so far. Then, let's see how the specification actually becomes an API gateway. Moon is not so much an API gateway server itself, as it is an orchestrator that configures the gateway. The top one is the data plan. User requests are received and passed through the RMMR server and client to the backend service. All actual traffic processing occurs in this area. The bottom part is the area for Moon. The YAML specification we wrote is converted into a configuration object, and Moon configures the data plane based on these settings. The settings can be read from central dogma or the file system. In other words, Moon is a control plane that defines and assembles how requests are handled, rather than processing them directly. Thanks to this, we were able to separate the traffic processing logic from the configuration management logic, and dynamic reconfiguration became possible. Now let's look at what each of these settings does. Moon settings can largely be thought of in three concepts. It is easier to understand what an API gateway does if we rephrase it as a question. First, what kind of request will it receive? Routes and APIs together fulfill this role. It defines which paths and methods to receive, and how to interpret requests as APIs. Second, where will we send it? We'll need a backend service to actually process these requests, won't we? The upstream handles this role. And finally, what happens along the way? Additional operations are expressed as plugins. Now, let's take a closer look at each of these. First, the route. A route determines who will handle a request when it comes in. The method and path identify the request, which is then forwarded to the connected upstream. It is similar to routing on a typical web server in the simplest form of an API gateway. However, in actual services, multiple endpoints often share the same upstream or authentication policies. However, in actual services, for example, get API users and post API users under the API. If we repeat this for every endpoint, the specification quickly becomes complicated. Therefore, in Moon, you can define routes in a prefix form. It groups endpoints to share common settings. We call such routes base routes. However, routes alone were insufficient to represent a REST API. Therefore, in Moon, we created a new concept called API. An API is very similar to a direct route in that it represents a single endpoint. Instead, it contains information similar to the OpenAPI specification for REST APIs. The API operates on top of a base route, inheriting upstream and plugin settings. And if necessary, you can also specify a different upstream in the API. For example, even for APIs under the same v1, some APIs can call REST services and others can call gRPC services. Next is upstream. Usually, when you hear upstream, you probably think of the backend server address. Of course, that is also correct. The most commonly used type is HTTP upstream. It's a typical API gateway that receives requests and forwards them to backend services. However, in Moon, we viewed the upstream a bit more broadly. We defined the upstream as a component that creates responses. For example, files return static files, and early return returns a fixed response. Sequential calls multiple upstreams in order. This can be utilized when combining multiple backend APIs to create a new API. And rolling updates are often used when performing large-scale migrations to an upstream, which splits traffic by a certain ratio. Ultimately, with Moon, it's not simply about where to send the upstream. It is a concept closer to how to create a response. So far, we have looked at concepts such as route API upstream. So, how do these components actually connect and operate? Moon operates on top of Armeria's reactive streams. When a request comes in, it passes through the server, then through the route and API, and is delivered to the backend via upstream in a continuous flow. The letters DATA on the screen also represent this flow. This represents data flowing along a stream in small chunk-sized units, rather than being gathered and transferred all at once. Therefore, the gateway doesn't necessarily need to hold the entire body in memory. This is because most routing or plugin operations can be performed by reading only the header. Thanks to this reduction in memory loading, we were able to secure a much higher throughput per unit of time. Up to this point, we have seen how a request is received, where it is sent, and how it flows in a single stream. Then, Gewan will continue to explain what happens along the way.
Hello. Hello, my name is Gyun Kim, and I will be continuing the presentation. Indeed, even with just routing or upstream, basic proxy functionality to forward requests to the backend can be implemented. However, an API gateway doesn't end there. In addition to routing, this is because there are common functionalities that need to be processed in the middle. Therefore, Moon separates these common concerns into a plugin structure. Each plugin operates as a decorator pattern, enveloping the entire flow. Requests are plugins. Requests are processed sequentially through plugins, and responses are processed in reverse order. These are the plugins that we support. We have finally divided each plugin to ensure it focuses solely on its inherent role. For example, initially, authentication might be sufficient. However, as we operate it, as the service grows, you may want to validate if the request is in the correct format and add logging or metrics for problem tracking. When traffic increases and you start to experience failures, that's when you add circuit breakers or retries. When should the response format be changed? It's a matter of plugging in mapping plugins. Whenever the 2,000 pound one requirements increase the existing code, instead of modifying, we combine plugins like Lego blocks. Naturally, you don't have to use only the plugins we provide. This is because user requirements can always vary. If needed, you can always create and add your own plugins. No matter how well designed a plugin is, it cannot perfectly address all requirements. In practice, operating a service, you may need to select specific fields from the back end. It often happens that we need to slightly change the structure of JSON before sending it down. However, every time there are such minor format changes, it is inefficient to create a new plugin every time. Ultimately, plugins were also code. Although we structured it nicely with YAML, it seems to be reverting back to code. So we created an expression language for Moon. Plugins define common behaviors. An expression language is responsible for detailed behaviors. The mapping plugin in the slide is an example. It can receive responses, extract only the desired fields, and reconstruct them into the required format. And as you can see, expression language also supports JQ-style data mapping. So, Complex JSON mappings can also be expressed relatively concisely. We can also connect plugins more closely with the API specifications. This means that the API specification can connect the schema with actual request and response traffic. Therefore, it's not that the plugin just sees JSON. It can even recognize what schema the data is defined with. For example, as you can see on the screen, the ID field has an attribute called xline ID encryption defined. This attribute is not just a simple setting, but rather metadata that describes what this field means. That is, this value declares in the schema that it is an identifier requiring encryption, not a general string. The plugin can interpret these declarations and operate accordingly. This means that when we process traffic and find the relevant schema, we can automatically encrypt the fields. The advantage of this method is that, instead of spherical code characteristics of data, that it can be expressed in the schema. Beyond simply describing data structures, schemas also. It becomes a medium for conveying the meaning of data. Even from the perspective of a plugin, there is no need to know individual API or field names. If you know what is declared, it can operate in the same way. This is just one example, and cross-cutting concerns like sensitive information masking or request response validation can be handled in the same way. Then, what actually happens when you add an API? I will now explain how changes are reflected in the API gateway after the PR merge, which is done in a Git repository like GitHub. Moon manages configuration data sources through an abstraction layer called property sources. The property source can be a file system or an external configuration storage. We operate a centralized configuration repository called Central Dogma. Moon is subscribing to the change events of this repository. When a new commit is reflected, Central Dogma synchronizes the corresponding changes. It delivers events to Moon. Moon reads the settings from Central Dogma, pre-processes them, and then binds them to a settings object. And based on this, we update our Maria's routing in real time. Then subsequent requests are processed based on the new settings. The actual traffic is processed by Armeria. Moon acts as an orchestra that manages and assembles configurations from above. This concludes the explanation of Moon, the Lotto API that identifies requests, Upstream, which indicates the destination to which the request will be delivered, and even a plugin that defines the operations to be executed in between. Moon has laid the foundation for providing API Gateway as a service to achieve this abstraction. So, from now on, I will talk about how this Moon has actually changed our way of working. Let's go back to that day I first talked about. Let's assume the same message was received. Could you please add one more API? However, our answer has now changed. Could you please refer to this guide and create a PR? Now, our team no longer needs to write code directly to add APIs. To create this structure, we organized recurring requests into a single standard workflow. The process of creating a PR itself is the same. However, who creates the PR and what is included in the PR has changed. The reason why only our team could modify the API was that the API was written in Java, a low abstraction language. However, now, we were able to write structured specifications based on YAML, and, thanks to this, people outside of our team can also contribute. The same goes for reviews. Previously, only developers could conduct reviews, but now the operations team also participates in reviews. Developers are now able to preemptively review operational issues that they previously couldn't see, and the merge specification is also used elsewhere. Documents are also created here. The information used by AI is also retrieved from here. So the process of changing APIs became more of a common process rather than a task for a specific team. One important change in this flow is that we can now check changes in an environment close to the real thing, right from the PR stage. When a specification change PR is uploaded, a temporary environment is deployed based on that PR. Although it has not yet been reflected in beta, the advantage is that you can actually run a server with the applied changes. Since API documentation is also rendered here, team members can discuss changes while viewing the documents included in the PR. From the reviewer's perspective, we can now review not only YAML or spec diffs, but also the actual execution environment and generated documents. As a result, it is faster. This means we have created a safer, collaborative structure. Let's see what results these changes brought. We believe there were three small certainties. Initially, there were immediate changes that were visible, such as in performance and operations, and as time went on, the way systems are built has begun to change. However, it didn't end there. As the structure changed, now we can utilize it in ways that were previously impossible. Let's discuss the first noticeable change. These are the changes that came out in the first iteration. That was performance. Based on the same server, throughput increased by nearly 3 times. Without increasing the number of servers, we are now able to handle more traffic. However, performance was not the only thing we gained. The biggest problem for line channel platform was cascading failures. Previously, if one upstream became slow, the capabilities have spread to the entire service. However, these four are now fine even if one of them slows down. This is because requests are processed in small units, and ongoing requests no longer occupy the thread. As a result, failures are not propagated, and the scope of impact is limited to the affected upstream. The second small but definite change is something that was not possible before, but became possible after we changed the system. The second representative example of small but certain happiness is documentation. In the past, API documentation had to be written directly on the wiki. Because we had to manage the old version and the documentation separately, it was not easy to keep the documentation up to date. However, in Moon, all API information is included in the specification. Thanks to this, without a separate documentation process, with just the specification, it became possible to display the API reference site. In addition, there may be requests to change the document structure over time. To easily support this, by introducing server-driven UI from the user's perspective. This allows for UI customization. If the UI is configured on the server side, it is a structure where the front-end's React engine renders it into appropriate UI components. As a result, the documents could be synchronized naturally. The burden on developers to manage documents has been greatly reduced. Even in operations, using synchronized documentation sites has changed the way we work. Whether you add or change an API, the first thing that changes is the specification. Then, Documents and operational information are also created from that. Teams no longer discuss APIs based on different standards. This is because everyone looks at the same specifications. The specification has become our single source of truth. Then I understand that the specification became the single source of truth. However, a question may arise. Ultimately, a specification is just a YAML document. If you modify the code and forget to modify the YAML, won't the same inconsistency occur? That's right, that's possible. However, the environment has now changed. When we used wikis as API documentation, it was practically impossible to check if the documentation and the actual implementation were different. With over 700 APs, manually checking all documents means that it was not realistic. Even if you confirmed it today, we could not guarantee that the same would hold true tomorrow. However, the specification written in YAML can now be utilized by the API gateway, actual traffic, and we were able to automatically compare specifications. For example, if the specification expects a string but actual traffic contains a number, then one of them is incorrect. Even if we just notify the API owner when such a discrepancy occurs, they can immediately verify it. This means that we are now able to actively detect and report spec inconsistencies, and that's for over hundreds of APIs, right? Of course, there can be temporary inconsistencies. However, what's important is that it's not that there are no inconsistencies, but rather that we detect them much faster when they occur. This means a system has been put in place that can restore it to the correct state. This is the last safety net. When we first designed the system, we didn't anticipate this aspect, but thanks to the system's structured nature, these are the achievements we were able to accomplish. It's AI. When we first designed Moon, we did not anticipate that AI would change our lives so dramatically. We also had to keep us with this change. We needed to enable AI to understand the hundreds of APIs in the channel. This is a continuation of the same story. Because there was already a structured API specification, we were able to quickly adopt AI support. It wasn't difficult to change the API specifications to Markdown. As a result, Gemini is now able to answer user questions based on the channel API documentation. A significant portion of the questions we received were about which API to use in specific situations. There are too many APIs. This is because users did not know what to use. Now, Gemini can understand the context and provide appropriate responses. As a result, we have been able to delegate repetitive API guidance tasks to AI and focus on more important work. And going a step further, we also created an MCP server. Directly within the developer's development environment through MCP server, we are now able to support code generation within a tool like Claude Code. You can directly query the API specifications of the channel platform via MCP. And based on that information, we were able to write the correct API call code. The core principle remains the same here as well. We simply provided the specification used in Moon as the MCP protocol because it was already structured. Converting to the MCP protocol had a low barrier to entry. Initially, it was a specification for building an API gateway. AI has now become the foundation for understanding APIs and supporting development. This was an even greater achievement than we initially anticipated. So far, we have reviewed the small achievements we gained from creating and operating Moon. At first, the API was faster. It began as a tool for safer additions. However, as time went on, what we actually changed was this was how knowledge about APIs was managed. This is what we call a system. Finally, let's summarize what we have learned throughout this process. We learned 3 lessons. First, consistency. As the number of APIs and teams increased, it becomes important for everyone to look at the same standards. Previously, the standards were scattered in code, documents, and people's minds. We gathered the standards into a specification and we created a single source of truth for APIs. Secondly, we have structure. It wasn't just about changing the format, rules that people implicitly understood. It was about transforming it into a system that machines could read, verify, and execute. Lastly, there is leverage. As the standards were structured, it became possible to utilize one source in multiple ways. With a single specification, run the gateway, generating documents. We were also able to connect with AI. It can also be called one source multi-use. The key takeaway for us was an approach that structured knowledge and enabled its utilization. The title of today's presentation was The Compound Effect of Good Design. What constitutes good design for us? The API gateway was expressed as a system called a specification. Over time, the specifications returned in various values. I believe that the value of structured information will become even more important in the age of AI. We hope that our experience today will provide a small hint for you in solving your problems. This concludes my presentation. Thank you for listening. Hello, everyone. Today's topic is the design of a media content ecosystem. I will be speaking on the topic Case Study on AI generated content integration. We operate centering on the CDP, how AI generated content was integrated into the media content ecosystem. I will introduce the design concept and business contributions. First, allow me to briefly introduce myself. I am Yasuyuki Tanaka. I belong to the Media Platform Division. I am usually in charge of the CDP that handles media content such as news articles. As a data director in the media domain, I am also responsible for developing data utilization infrastructure and promoting governance. I myself have spent most of my career in the field of search technology and data infrastructure. Therefore, how should content be held in what form? I believe that will determine its scalability for many years to come. Today, I would like to explain such design decisions and our efforts to properly govern content data. Good day. I will speak in the following order. First, as background, I will explain why it was necessary to integrate AI generated content into the ecosystem. Next, as an overview of the ecosystem, it is centered around the content distribution platform. I will explain the content's cyclical structure. Next, regarding the system design, I will specifically introduce the three main platforms and their collaborative architecture. After that, business contribution, platform operations. I would like to conclude by discussing future prospects. First, I will explain the background. First, what exactly is AI generated content? Generally, regarding the differences in content for articles submitted by a media company. We aggregate comments and reactions to specific topics or angles. This refers to content generated by AI in the form of articles. In media services, including Yahoo News, in addition to article content, we are now also providing AI generated article contents. To introduce specific examples, the first is a comment article. This is a summary of comments submitted to Yahoo News, organized by AI. The second is Buzz Summary. This is an AI generated trend from Yahoo Real Time Search. It will be aggregated content. It offers a different perspective than articles written by journalists. This initiative aims to broaden the range of information users can access by delivering insights into public reactions and trending topics. Next, I will explain why we integrate AI generated content into our content ecosystem. So, among the services provided by Inafusa, those that particularly handle article content are there are many services such as Yahoo News, Line News, and the Yahoo Top Page. I introduced earlier AI generated content as well. These are pieces of content generated by different services, Yahoo News and Yahoo Real Time Search. Suppose each service has its own content management and distribution system. Those, we want to link content between services and distribute it. Please imagine such a scenario. Whenever new content increases, individual support is required for all services that reference the submissions. I don't think it's realistic to implement that. That is why we centrally aggregate diverse content. There is an ecosystem as a platform that can distribute, search, and analyze. The goal we aimed for this time was to integrate AI generated content into this ecosystem. On top of that, various services can be used and deliver content to users faster. And the platform is responsible, including managing the terms of use. Our goal is to establish these three things. What is the approach for that? Instead of adding a new dedicated pipeline for new content formats, it was about extending it. The integration of new content formats into existing ecosystems. It sounds simple when you say it. Before focusing on the technical implementation, we needed to pass three discussions. The first is data governance. It has become necessary to confirm the conditions under which data can be handled. Here, for AI generated content, we organize the legal and contractual handling of original data and generated products, and determine the scope of integration. The second is integration with the platform. This is about aligning the constraints of existing infrastructure with new requirements. Existing infrastructure has usage restrictions that have been established through many years of operation. This is the process of deciding where to align with existing specifications and where to extend them. The third is coordination with ecosystem stakeholders. Because content owners and users each have their own requirements, the platform adjusts not only technical specifications, but also terms of use and operational policies. Only after these steps is technical registration initiated. Conversely, if the design is sufficiently abstract, then the technical work after obtaining these discussions can be minimized. This is why we chose the approach of extending it. Next, I will explain the overview of the content ecosystem. Against this backdrop and through these discussions, I will now explain the overall picture of the content ecosystem into which AI generated content will be integrated. First, I will explain the scale of ecosystem utilization. Currently, 14 internal services submit content. This includes the Yahoo Japan app and Yahoo News, with 36 services, referencing the search and recommendation APIs. There are a great number of services available. This system consists of three main platforms. The first is the CDP. This is a platform for aggregating, distributing, bidding, and searching content. The second is the feature analysis platform. This is the foundation for extracting the meaning of content. The third is the search platform. This is an engine that responds to search recommendations. At the core of this ecosystem is the CDP. To manage ingested content, it collaborates with other platforms to establish the flow of the entire ecosystem. I would like to show you how these three are linked in the next diagram. This is a diagram illustrating the overall flow of the ecosystem. Content is submitted to this CDP from in-house media services, such as Yahoo News. Next, we perform content feature analysis. This configuration suggests content is recommended through search and then returned to the client. Then, the client logs the delivery results distributed to end users, which are then used for analysis and improving delivery logic. The core of this mechanism lies in two elements: content ID, and content schema. A content ID is assigned upon submission and is used consistently across all processes, from feature analysis to search logs. Content schema. It is a unified data structure defined by the content delivery platform, serving as a common language for all platforms. And one more thing I want to emphasize is this feedback loop. User browsing and compounding remain in the logs with a content ID. After analyzing the effects, we return to the search keywords. As this loop continues to turn, we aim to ensure that the delivery frequency is maintained. As for the overall architecture, there are two main data flows. The process of content submission is from the left in the diagram, when content is submitted to the right. The content delivery platform is receives data. We analyze it using a feature analysis platform. We index content and features into the search platform. The content delivery system flows from right to left in the diagram. Then, the backend system of the utilizing service sends a search recommendation request to the search platform via the API of the CDP. The three platforms appearing here are this is a key player supporting this ecosystem. The three main components supporting this ecosystem. Store and organize. I will organize this from the perspective of utilization. First, the content delivery platform is responsible for storing content. Here, we manage and integrate the content submitted and coordinate with each platform. Next, the feature analysis platform plays the role of organizing. We extract the meaning of the content and add various features to it. And the search infrastructure plays the role of utilizing these. Here, content and features are indexed to respond to search and recommendation queries. These three phases of accumulation, organization, and utilization, the content ecosystem functions through the collaboration of each corresponding platform. Next, as for the system design, I will now specifically introduce the search platform, which is a key player. First, the CDP. And content schema. This defines the field structure, such as content title, body, and metadata. And the feature analysis platform. The search infrastructure is also built upon this content infrastructure. As I mentioned in the previous slide, this is the common language used throughout the entire ecosystem. The second is content lifecycle management. As for content lifecycle management, updates to articles after they've been submitted, or deletion at the distribution deadline, which is responsible for managing content states. The third is the distribution system. It also functions as a gateway for the search infrastructure. This controls the request volume from each service. More details will be provided later. Next is the role of the feature analysis platform. The feature analysis platform, as I mentioned earlier, is a platform that extracts the meaning of content. There are mainly three types of features used. The first is category. This is a classification of content topics. The second is entity extraction. This shows the entity information and the degree of topic relevance included in the content. It holds such pair information. The third is category vectors. This is an embedding vector that numerically represents the meaning of the content. Related to today's presentation, category and content vectors. Categories will be used for refining searches and recommendations. Content vectors can be used for recommendations and searching for similar content. Even for AI-generated content, we use the same analysis pipeline as for article content. Even if the content formats are different, they can still be treated as content with the same metadata from search recommendations. This is the premise for extending the existing pipeline. The component that we have been referring to as the search foundation up to this point, this is the system we call ABIS internally. This is an Apache Solr-based search engine platform. We also introduced this at Tech Fairs 2022. Some of you may already know this. Here, both the content that has been ingested and the features assigned by the feature analysis platform are imported into the Apache Solr index. For search areas, recommend query and returns relevant content for requests. For services that utilize content, the crucial point is that both original articles and generated content can be handled in the same way. I will now explain the key points when integrating the AI-generated content into this ecosystem. The first is about data handling conditions and content management rules. We have also confirmed with the legal department that it complies with laws and contracts under the same rules as existing content. We have confirmed that there are no issues with integrating it into the ecosystem. The second is compatibility with existing content schema. Regarding AICC content, the data structure was not exactly the same. We were able to accommodate this by mapping it to the existing content schema. For example, if we take the buzz summary as an example, there are no publishers involved. We do define such fields, but this is because it cannot be applied to AI-generated content as is. We implemented measures such as matching strings representing buzz matome. The design policy was consistently planned. Instead of creating new types, we will leverage existing pipelines. This is because the existing gaps were abstracted to such an extent that they could absorb new forms of content. We were able to expand it. Next, I will explain our business contributions. I will explain what value and results were obtained. I will discuss the business contributions of this initiative. From the perspective of the three companies' services, primary articles, comment articles, and buzz summaries, these are delivered as results from existing search recommendations. As for specific use cases, Yahoo News is available on the Yahoo Japan app and other platforms. We are able to post comment articles and buzz summaries on the existing main article timeline. This allows for diverse services available, deliver content to users more quickly. This means we were able to achieve this. I'd like to discuss another initiative and its results from a platform perspective. The Content Delivery Platform, CDP, is a distribution network already widely used by both content submitters and referrers. This time, we were able to place AI-generated content directly onto this existing distribution network. As no individual development was required and existing users did not need new onboarding, the ecosystem is structured to accept new content formats with minimal cost. This demonstrates the validity of our approach to extending existing mechanisms. Next, I will discuss platform operations. Specifically, regarding the content delivery platform, what was the thinking behind this large-scale system? I will explain how we operate. First, as a platform team, we are aware of it functions as a bridge between content owners and content users. The content owners on the input side and the content user, who is the user, each has different requirements. For example, content owners want to know if the content they have submitted is being used appropriately. Content users want to deliver content to users as quickly and effectively as possible. That's how it is. The content distribution platform plays a role in mediating the requirements of both sides, specifically, onboarding new services and adjusting schema requirements. Yesterday, we addressed additional prevention measures. These are the specific tasks that act as a bridge. And as a platform responsibility, how to handle this content. I will explain how we manage this permission. The content that was originally submitted was. This is handled by the submission service and the contracts with media companies. If an in-house service wants to use that content, checking content usage permission becomes the responsibility of the service that uses it. The platform verifies whether confirmation has been properly carried out. We operate by confirming the acquired float approval and then releasing the ACL for content usage. By doing so, we prevent usage from starting without proper authorization. This is not a technical challenge, but rather a responsibility that the platform should bear as an operational mechanism. It's not just about distributing content, but also about ensuring that it is handled appropriately. We believe this is also an important responsibility as a bridge builder. Finally, I would like to introduce two system operation innovations for platform operation. First, we have implemented cluster separation and rate limit settings for each reference service. This is media-related services are it is characterized by very large fluctuations in load. Normal operation, also, there are peak and off-peak hours. Furthermore, in the event of push notifications related to life and property, such as earthquakes or tsunamis, we may experience several times the normal peak request volume. The load flowing into a certain platform should not affect other services. And it's easy to isolate the scope of impact in the event of a failure. This is why they are separated by service. The second is the clear division of responsibilities when extending functionality. There are often requests for new feature additions. In that case, is this feature a common feature used by multiple users? Or is it business logic specific to a particular service? First, I will ask about that point. Even if it appears to be a service-specific behavior, if it is determined that multiple users will use it, we have made the decision to provide it as a configurable feature for each service used. Finally, regarding future prospects, how will this ecosystem expand? I will now explain our future initiatives. One of our future initiatives is this is about the Line News Content Initiative, integration. The content delivery platform is this platform was originally built on the premise of Yahoo Japan's services. Content schema is also limited to the Yahoo Japan service format. In integrating Line News, we aim to support a wider variety of formats. We plan to expand content schema. We consider this the first step in expanding the ecosystem to line-related services as well. The second initiative is the addition of the MCP interface. MCP is a standard protocol for interfacing with generative AI. Currently, the AI and API of the content delivery platform it is assumed to be used from the service's backend system. By adding MCP as an interface here, our internal AI agent through the CDP, media content can be directly utilized. This is what we are thinking. This is not limited to adding interfaces. It also expands the content ecosystem users from service backends to AI agents. The design assets of content schema and content ID are also used for calls from AI agents. I believe this is an initiative that will come alive in an interpretable way. Finally, I would like to summarize 2 points of what I have told you today. The key to this content ecosystem is a common ID for service consultation and good content schema design. New content formats also use the same schema, the same pipeline. We were able to use the same platform and decided to treat AI-generated content specially during the provision. The second is the platform, and also a role in promoting content utilization. It also acts as a gate to ensure compliance with the terms of use, acting as a driving force for the utilization of content across many services. We will expand the fixed scenario. Both of these are the platform's responsibility. That concludes my presentation. Thank you for listening. Then, Narukawa Minoji Misa will give a presentation on the efforts of confidential VM to ensure the privacy of Line Yahoo's AI functions. Hello again, I am Narakawa from the Cloud Infrastructure Unit. I usually work on low-level virtualization tasks. Today, I will explain the mechanism of confidential VM. I am Minoji from the Cloud Infrastructure Unit. I am usually involved in GPU virtualization and related areas. Today, I will explain the implementation of confidential VM from an IaaS perspective. I am Misawa from the Server and OS division. I am usually involved in the operation and maintenance of OS for internal servers. Today, from an OS perspective, I will explain our efforts to run applications on confidential VM. In this presentation, I will first explain the objective, then the concept of confidential VM. I will explain our implementation on OpenStack in our cloud, and finally, how we trust applications. First, I will explain the purpose of this presentation. Line Yahoo provides services that utilize AI. Some of them involve the input of users' private information. Therefore, on the cloud infrastructure, to process such data, a high level of security is required. Of course, as Line Yahoo, operating in a secure data center is a given, but a security model that doesn't even trust the hypervisor would provide even greater security. Line Yahoo internally provides a private cloud called Flava. As an integrated in-house cloud, we provide various services such as IaaS and PaaS. For IaaS, we use OSS called OpenStack. This time, I will talk about the in-house implementation and provision of confidential VM to improve the security of AI functions. There were actually examples where confidential VM itself was being used. On the other hand, Line Yahoo's private cloud uses OpenStack, but OpenStack did not have the necessary features. Also, there wasn't a general method to attest to applications. Next, I will explain what a confidential VM is. Confidential VM utilizes CPU functionality to create an isolated VM environment. Utilizing AMD's SEV SNP feature, you can run isolated confidential VM in the form of a VM. The contents of the VM are also encrypted and isolated from other processes running within the same hypervisor. Intel also provides isolated confidential VM in the form of VMs, using a feature called TDX. This time, we will explain confidential VM, which provides secure processing based on SEE SNPVM. This diagram shows the overall picture of the system we will be explaining today. I will explain them in order. First, regarding the bottom left part, I will explain how the smartphone application securely communicates with confidential VM. The goal is to enable the Line app to establish a secure channel with confidential VM and securely send private information. This is the overall picture, and I will explain each one. This time, there is a premise that the hypervisor is considered untrustworthy. Many might find it counterintuitive that we, Line Yahoo employees, would not trust the hypervisor operating in Line Yahoo's data centers. But to achieve higher security, in order to protect what we want to protect, it is important to clearly define the minimum areas that need to be secure and to minimize those conditions as much as possible. This time, in order to protect Line's very important message information, Line Yahoo's hypervisor, instead of relying on that premise, we envision a configuration where the smartphone application itself ensures its own security. We aim to create a system where even Line and Yahoo employees operating the hypervisor cannot read the information input into the AI. Next, I will explain why smartphone apps can trust confidential VM. To verify what a confidential VM is, we use something called an attestation report. This is what lies beneath the non-shifting confidential VM. I will now explain what this is. The attestation report records a SHA-384 hash value called measurement. This is the SA384 hash value representing the memory state loaded at the time of VM startup. If these match, then we know that what was loaded at VM bootup is the same. Then, for example, if the measurement of when it started up as expected is recorded and incorporated into the smartphone app in advance, this means that a VM with the same measurement value has booted as expected. On the next page, we will explain this attestation report. So, what specific data does the VM state included in the measurement contain? This would be the initial memory state of the VM. With a regular VM, the BIOS is included, but I don't think there's usually much to be learned just by looking at the BIOS. This time, we will use something called direct kernel boot as the VM boot method. In this case, before the VM starts, not only the BIOS, but also the kernel and kernel options are expanded into memory. It directly boots the kernel. In this method, the attestation report's measurement target configuration includes not only the BIOS, but also the kernel and kernel options. Also, even without actually launching it, if the necessary files such as the BIOS, kernel, and options are available, you can calculate what the measurement should be. Therefore, if this matches the hash calculated by a trusted BIOS, Linux kernel, and kernel options, then the issuer of the attestation report is able to confirm that. We can confirm that the kernel and kernel options are running as expected. The attestation report itself is issued by the AMD processor, and at that time, an electronic signature is affixed by the CPU's key. Using this, we can verify whether the attestation report was issued by a legitimate AMD processor. For verification, we check whether it can be verified with certificates published by AMD. Up to this point, the contents of the attestation report can be trusted, and with the measurements within it, the contents of the VM can be understood, and thus the contents of the confidential VM can also be trusted. Assuming the issuer of the attestation report can be trusted, how can we securely communicate with the issuer of the attestation report? The attestation report has a field where arbitrary data, such as a public key hash, can be embedded. By embedding the public key hash, smartphone applications can use this public key to establish a channel of engagement with the confidential VM, which is the issuer of the attestation report. So far, smartphone apps I have explained up to establishing a secure channel with a trusted party. So, what would happen if the system were tampered with? What would happen if the server were attacked and the VM compromised? I will explain. Using three patterns. First, it's when the VM configuration is changed. For example, if the kernel is replaced with one containing malware, or if the kernel options are replaced with something different from the original. This refers to it. In this case, the measurement will change. Therefore, the measurement value recorded in the attestation report on the right side of the diagram will change, and from Smart Fanfly's perspective, it will become an unknown hash value. We can detect tampering with the VM. If it is detected that the party with whom the secure channel was to be established has been tampered with, the smartphone application can cancel the transmission of sensitive information. In this way, if the VM is compromised and in its original state, the smartphone app can detect it before transmission and cancel the sending of sensitive information. The second case is when the attestation report was not issued by a legitimate AMD CPU. This includes cases where an attempt is made to forge the attestation report by tampering with the CPU to report different measurements than the actual ones, or when the CPU is not a legitimate AMD processor. In this case, since an electronic signature verifiable with AMD's key cannot be created, the attestation report itself, it will be detected by smartphone apps as a fake that fails verification. In this case, too, we can detect it before transmission and cancel the sending of sensitive information. The third scenario is when an attacker attempts to impersonate a server using an attestation report legitimately received from a confidential VM. In this case, the attestation report itself will pass validation as a legitimate report, and the measurement will also be correctly listed. However, in this case, the smartphone app will attempt to establish a secure channel using the public key of the real VM that issued this attestation report. The corresponding private key exists only within the confidential VM. Therefore, since there is no choice but to use a different key, the public keys will not match, and thus a channel will not be established with the attacker's server. In this way, the smartphone app can detect that the recipient is not the expected confidential VM before sending, and thus cancel the transmission of sensitive information. In this confidential VM configuration, when a smartphone app connects to the confidential VM, the VM is running on a legitimate AMD CPU, and we can confirm that the kernel is operating as expected without any tampering, even considering the possibility of destruction. On top of that, we can establish a secure channel and send information externally securely. Next, I will explain how to implement confidential VM using Flarman's OpenStack. In implementing confidential VM in Flava, we carried out the following 2 points. The first is to enable the launching of confidential VM. Since OpenStack did not support SEV and P, we implemented it to enable confidential VM to start. The second point is that we enabled pre-configuration of the BIOS, kernel, and kernel option using a mechanism called direct kernel boot so that an attestation report can be obtained and verified. Furthermore, we passed the certificate to the VM so that the attestation report could be verified. So far, we have discussed the overall picture, and from this point on, we will explain the right-hand box that includes the hypervisor. First, I'll talk about the first point we implemented, enabling confidential VM startup. We have implemented SNP compatibility in OpenStack by passing settings to virtualization middleware called libvirt. By implementing it in this way, users will be able to launch confidential VM in the same manner as regular VMs. Please see the confidential VM startup method example in the next frame. As for changes, we will adapt the OS image for confidential VM and change what is called the flavor, which represents the number of CPU cores and memory capacity, to confidential VM. And then, we pass the user's application container image as an additional parameter. In this way, the confidential VM can be started. In the next slide, in addition to the SEV's SNP implementation, I'd like to introduce the necessary changes and our upstream contributions. Since the hash value of the container image and other information were required as kernel parameters for the official confidential VM, the character limit for kernel parameters handled by OpenStack was exceeded. Therefore, we extended the options passed to the kernel to allow strings longer than 255 characters. The content I have described so far in the slides is currently in OpenStack AppStream. We are moving forward with proposals and bug reports. We plan to release our development documents and source code, and in the future, we hope to make this functionality available to external OpenStack users as well. Above, I have described the implementation up to the launch of confidential VM. From this point on, I will explain the mechanisms necessary to make the attestation report verifiable. First, to verify the attestation report, as I mentioned earlier, it is necessary to use direct kernel boot. Please take a look. When creating a VM, we create it using an OS image. So with a regular VM, we only use the OS snapshot as the OS image. However, with confidential VM, in addition to the OS snapshot, the VM BIOS, kernel, and kernel option are explicitly handled as a set in the OS image. In addition, we allow users to launch application containers and a specific container image separate from the OS image. This separates the OS image creation timing from the user application creation timing. We guarantee that neither image has been tampered with by a third party. In the next slide, I will now discuss certificates. Excuse me, when NPM validates the attestation report, we use VC certificates. These are necessary when verifying that an attestation report is genuine. Also, a unique VCX certificate is issued for each CPU chip and can be obtained from AMD servers. We made sure to store the VCIC on the physical server in advance. There are two reasons for this. One is that VMs are operating in an environment isolated from the internet and cannot access the AMD server. The second is to enable the acquisition and verification of the attestation report even when the AMD server is not operating. Thus far, we have explained the mechanism for verifying the attestation report from the VM user, as well as how to implement confidential VM using OpenStack and Flava. From this point forward, I will discuss how to deploy applications that provide services. Service applications deployed on confidential VM. This makes the application on the user's side trustworthy. This means that the user's application can decide whether to communicate with that service and promote sensitive information. The deployment of service applications that I am about to explain is a part of the overall system. This is the area within the confidential VM, as shown in this bubble. The fact that the kernel parameters are included in the attestation report measurement, which was explained in the first half of this presentation, becomes important for verifying whether it is a trusted service application. For more secure communication between mobile applications and service applications, which is our objective, the service running within the confidential VM, it must be in a trustworthy state for the user. What exactly is a trustworthy state? Then I will explain how we achieve that. So what exactly is a trustworthy state for a service running within a confidential VM? In this initiative, we define a trustworthy service state by the following two conditions. First, the service starts without the specified content being altered. The second is that services are not altered after startup. As shown in the center of the diagram, the service here consists of the OS and application containers. In other words, the goal is for the OS and application container to launch exactly as specified and remain unchanged after launch. If these two conditions are met, users can make trust judgments based on the service actually running. So how do we achieve this state? In this initiative, we have achieved a trustworthy service state through two mechanisms. The first is the specification of services through kernel parameters, as shown on the left side of the left diagram, and this is a mechanism to link it to the attestation report. We specify the OS and application containers using kernel parameters and reflect that information in the attestation report's measurements. This allows the client to verify which OS and application containers have been launched. The second is the OS configuration to prevent external tampering after service startup, as shown on the right side of the diagram. This allows the service to remain in an unaltered state after startup. Next, I will explain how to specify and launch services using kernel parameters, and then I will discuss OS settings to prevent post-launch modifications. As shown on the left side of the figure, we embed hash values representing OS and application containers into the kernel parameters when confidential VM is launched. If the content of the OS or application containers changes even slightly, their hash values will also change. Each hash value is referenced by tools such as dmverity and our in-house container launcher, as shown in the center of the diagram. Additionally, our in-house container launcher refers to the digest of the container image. It retrieves and launches a container with the content specified by that launch value. On the next slide, we will explain which tool handles each hash and how. dmverity is a tool that can detect changes in the contents of the root file system. The OS updates so far actually refer to the root file system. As shown on the left side of the diagram, the root file system contains all the software necessary for running the service. For example, libraries and configuration files. dmverity provides a root hash as a representative value for the entire root file system. As shown from the left to the center of the diagram, if even a part of the root file system's content changes, the content of the root hash also changes. If the content read from the root file system changes while the Linux kernel is booting, subsequent processing can be stopped. With dmverity, the root hash value is specified in the kernel parameter. Therefore, as shown from the center to the right of the figure, the contents of the root file system will be included in the attestation report's measurements. This means that clients can verify which root file system the service is running on. By utilizing these functions and presenting the root file system to the Linux kernel as read-only, this ensures that the root file system, which the client expects, boots without being tampered with. On the other hand, if the root file system is presented as read-only, changes required for service startup will also become impossible. What to do about that will be explained on the next slide. In the operation of this confidential VM service, it's not that no files are written after the confidential VM starts. For example, there are rights necessary for providing services, such as acquiring container images or generating temporary files. Therefore, we use overlay.fs to layer a writable memory-based layer on top of a read-only root file system. Although it appears as a normal writable file system from the service, actual changes are stored in an overlay layer in memory. The root file system itself, protected by dmverity, will not be modified. Therefore, if there are no changes, the content will be read as shown on the left of the figure. If there are changes, they are saved in memory as shown on the right, and the content is read after the changes have been made. This mechanism allows the service execution platform to remain unchanged while still accommodating necessary service modifications. Additionally, the hash of the root file system targeted by attestation also does not change. Up to this point, I have explained the details of the OS for services running on confidential VM. Next, I will explain application containers. The contents of application containers can be verified using the digest hash of the container image. As shown from the left to the center of the diagram, if any part of the container image content changes, the hash of the container image also changes. As shown in the center to the right of the diagram, by including this container image hash in the kernel parameters, changes in the container image will be reflected in the attestation report measurement. Therefore, clients can verify the contents of the container that started before sending data. Next, we need to actually launch the service application container using this hash. I will explain the boot mechanism next. Application container startup is. This is performed by the service application launcher located at the bottom center of the diagram. First, the launcher obtains the container image digest included in the kernel parameters. Next, it retrieves the container image specified by that digest from the container image registry and launches it. Here, the service application launcher is contained within a root file system protected by dmverity. Therefore, the launcher itself also starts without being modified. As a result, using a container image digest. The specified application container is also launched exactly as specified. Up to this point, I have explained that we can achieve a state where the OS and application containers can be launched without modification to the specified service content. Furthermore, the attestation report now allows us to verify which OS and application containers have been launched. To make the service trustworthy, we must also ensure that the service cannot be altered after boot, which is the other condition. What the attestation report guarantees is the state of the confidential VM at startup. If one were to log into the OS after booting, by changing settings or replacing binaries, the state confirmed in the attestation report can be altered. Therefore, we prohibit access after a confidential VM is launched. Specifically, SSH login and console login are disabled. Therefore, it is not possible to log into the OS and perform operations after confidential VM starts up. As a result, we have achieved a state where users, such as clients, can trust the service. On the other hand, even if users cannot SSH, as I've explained, they can launch applications simply by specifying the container in the kernel option. First, we explained that by utilizing the attestation report provided by SEEE SNP, a secure communication channel based on attestation can be established between a confidential VM and a remote client. Next, we introduced the implementation for using SEVC SNP confidential VM on OpenStack. We are developing features to create and manage SEEV SNP VMs from OpenStack, and we are also working on contributing those results upstream. Finally, I introduced a mechanism to extend the scope of trust, not only to the confidential VM itself, but also to the application containers running within it. This concludes our presentation. Thank you very much.
everyone. Thank you for joining us today. My name is Javier Luca de Tena, and today here with my teammate Tsuruhara Tomu-san, we are both server-side engineers at the line messaging dev team, and today we are sharing how we are transforming the line messaging from the active standby disaster recovery model to a fully active multi-data center system. This session is about what we are building and what we have learned so far. This session consists in two parts. I will be talking first, the first half, about the line messaging and the active standby architecture, what limitations that we have faced, and why we have decided to move to an active architecture. He will also be sharing about some of the solutions that we have thought and some of the challenges that we are facing. Then Tsuruhara-san will take over and talk about why we need a new database to make all of this work. For those unfamiliar with the line messaging, it's one of the most widely used messaging platforms in Asia, serving hundreds of millions of users globally and processing billions of interactions every day. It's not only about text messaging. It has voice and video calls, rich media, stickers, and much more, and also a whole ecosystem of applications built around it. Line is a critical communication infrastructure, so reliability and performance are fundamental for us. So here is a simplified overview of our architecture. Clients connect through our API gateway to the messaging backend, which handles all the traffic logic, messaging like messaging delivery, synchronization, social graph, etc. And the backend relies on a storage layer, which is compounded by Apache AceBase for the persistent data and Bulky, which is a Redis fork for the caching layer. All of this is operated in our private cloud called Flava, and so this means all infrastructure is managed by us end-to-end. As the API gateway is already an active component, for today's session we will be focusing on the messaging backend and the storage layer. First, let me explain about the active standby architecture and what are the limitations that we are facing. Our current disaster recovery model is a classic active standby setup. So one data center handles all the traffic. Data is replicated asynchronously to the standby data center, holding a whole copy of the data. If the data center goes down, all the traffic is switched to the standby. This is a very simple approach, and it has worked for us for many years. But this model has serious limitations. Let me give you a real example. So we perform regular disaster recovery drills where we simulate a whole data center failure and validate that things still working. During one of these drills, we discover a core feature has been broken in the standby for weeks. Nobody noticed because the standby never receives real traffic. So here's the fundamental problem. So the standby is invisible. It cannot be tested with real conditions, so it degrades silently. And if you don't want this to happen, maintenance costs can grow quite a lot because every new feature will need disaster recovery support included into the drills and dedicated testing. Failover also requires some service interruption to restart the process or changing the configurations or maybe warm up the cache. And we are paying for a whole data center that it sits there doing nothing most of the time. However, all line core features must work regardless of any data center outage with close to zero downtime. So we ask ourselves, why just not have both data centers as active, sharing everything in an active fashion? So then there will be no invisible standby that silently degrades. Both sides will be always validated with real traffic. No cold start, traffic just shifts to the surviving data center, and service continues. That is how we achieve downtime close to zero. But as you will see, this is not easy. So you might think, why not just make both the data center actives and share everything? The problem is, well, physics. Our data centers are geographically separated, so latency naturally increases. So for simplicity, let's say 20 seconds for the whole round trip between data centers. And that, compared to 1 or 2 milliseconds that we have in a single region, is a big gap and creates very real challenges, as we will see next. The first challenge is data consistency. With asynchronous replication, regions can temporarily see different values. Imagine a write in region A may not be visible yet in region B, causing stale reads. Many services can tolerate this and move in this model, but in a real-time messaging service, many users-facing operations like messaging ordering, friend list, conversation metadata, privacy settings, or group membership, depend on seeing the latest state. And stale read can directly translate into confusing or incorrect behavior for the users. So, and under high load or network problems, the replication lag can grow and the issue will be even worse. So our solution is to adopt a region partition active-active architecture. The key idea is very simple. We assign each piece of data a primary region. All reads and writes for that data are routed to this primary region. And this eliminates the stale read that we have mentioned before. Of course, data is replicated to at least 2 data centers for resiliency. And we also have a third data center that is for storage purpose only to handle consensus and durability. But that will be covered by my teammate Harasan later. Under normal operation, both active regions serve users independently. If region B fails, all traffic shifts to region A automatically. Region A was already active and well tested with real production traffic, so we have high confidence that it will work correctly. Of course, there will be additional traffic going to the surviving data center, so we make sure it has enough capacity. We can also partition our data based on the communication patterns. Users naturally tend to communicate with other users in the same geographical area, so their data can live together in the same region. With this, we can keep most of the traffic within a single data center or in the single region, so the cross-region latency penalty is significantly reduced. But you might be wondering, how do we route to the correct region? So to solve this, we are building a new component called that we have named Region Lookup Manager. It answers one question. For a given piece of data, which region is the primary? When the service needs data, it first asks to the Region Lookup Manager which region is the primary, and then the service goes directly to the primary region where the data is always fresh and consistent. The Region Lookup Manager is deployed in every data center as an active-active component, so queries are always local and fast. The region mapping is stored in a consensus-based storage that guarantees mappings are never lost. Even if one data center goes down, the surviving 2 still have the majority and keep serving. We are also adding a caching layer that we believe will be really effective because region mappings change very rarely. But even with geographic partitioning data, cross-region requests are unavoidable. Users in Japan may message friends in Thailand, or maybe we have groups spanning multiple regions. So a single request may need to query data from multiple regions. So the issue is that a single API can trigger multiple sequential I/O operations locally at 1 or 2 milliseconds. Well, it works fine and nobody optimized, right? But across regions, each I/O can take around 20 milliseconds, easily breaking the service level objective and, of course, degrading our user experience. So just to visualize, let's say a group message may require fetching the group information, then the member list, the delivery preferences, maybe privacy settings, client information, sender profile, then maybe store the message and update the inboxes for everyone. This could mean many sequential I/O, making latency a real concern. To address this, we are optimizing I/O in different ways. First, we parallelize and batch operations whenever possible, using custom tooling that we have built for safe parallel I/O. It sounds straightforward, but proving I/Os can be safely parallelized in a high concurrency system like line messaging requires deep analysis of the code paths and distributed traces. Ordering assumptions that held at 2 milliseconds may break in subtle ways at 20. So we also merge data models when it logically makes sense, combining data that always fits together into a single query. This actually increased the schema coupling, but the latency and the I/O reduction, I think it justifies the trade-off. Let me show you the actual impact. So this is our response time service level indicator for group chat messages over time through multiple optimizations. And as you can see, it has been dramatically improved. Sorry. The next challenge is bulky node-to-node replication. And this may require a further explanation. Bulky keeps a buffer of recent writes for replication. Locally, this works fine. But across regions with higher latency can cause replicas to fall behind. When these replicas fall behind, bulky triggers a full synchronization and transfers the entire data set. At the line messaging scale, hundreds of shards could trigger full synchronization at the same time, saturating the network, causing even more replicas to fall behind, and then we have a cascading failure. Full sync is also a resource-intensive thing and can impact the normal traffic handling. And because all of these reasons, we have decided to not replicate bulky across regions. So data belonging in one region is simply not cached in the other. So imagine region B goes down. Traffic shifts to region A, but region B's data is not cached there. So every request now falls directly into the persistent layer, and it cannot handle all the traffic by itself. Then the persistent layer gets overloaded. Region A starts degrading too, and what we thought it was a single region failure became a two-region outage. We thought about multiple solutions for this, one of them being a bad job to pre-populate the cache. But then we won't be able to switch the traffic until the job is completed. So it will require service interruption, and we'll be back to square one. So what we need is to keep cache warm in the other region continuously and with enough consistency so failover can happen instantly. And to solve this, things like simple read-through cache in the other regions is really not an option, because maintaining real-time consistency across regions without any transaction is not feasible. Transaction algorithms, such as two-phase commit, will add latency to every cache write, not to talk about the amount of complexity it will bring. So we need something different. And what we came up with is a solution with using asynchronous event streaming. For mutable data that uses read-through cache, such as user information or social graph, after our caching transaction algorithm commits into region A, we publish the results into Kafka. A consumer in region B reads it and writes it into the region's B cache. Since Kafka messages can arrive out of order, we use a transaction ID. So we only write into the cache if the transaction ID is newer. If in case of producing an inconsistency, that can happen, it will eventually disappear thanks to a configure TTL. So as you can imagine, this has many edge cases outside the happy path. So the consistency isn't actually perfect. But considering our goal is instant failover, we consider this a fair trade-off. For immutable or write-through cache data, we can use change data capture, where we stream the mutations entirely directly from the persistent layer write-ahead log. We have another challenge. The messaging backend is already facing a fair amount of complexity. We have multiple database middlewares, each one with their own APIs, clients, or operational quirks. On top of that, the services are implementing sophisticated caching algorithms, secondary indexes, transactions, fallback logics that cascade through multiple layers. This complexity has made our developers to introduce subtle bugs that in some cases has led to, well, production incidents. Now, we are adding even more complexity, consensus-based storage, multi-data center routing, the region lookup manager, cross-region cache warm-up, and failover handling. Expecting every service team to implement all of this correctly, consistently, and without bugs is probably not realistic. And keep in mind that we have shown today just the high-level overview. So this is why we are building the storage abstraction layer. It sits between the service and the storage and expose a simplified, unified API. Developers do not need to know which region owns the data, how caching is implemented, how warm-up events are produced, or how failover is handled. All of that is handled transparently inside the abstraction layer. This makes migration to the multi-region active-active architecture seamless. Well, not seamless, maybe less painful. So let me recap. We are building region partition active-active system. We have solved the I/O penalty, the region routing, hidden the complexity behind an abstraction layer, the cross-region cache warm-up. All of this gave us the architectural model to achieve almost instant failover and more robust disaster recovery model. But when operating bulky and ACE-based across regions, we found that they have some limitations. They were not designed for native multi-region data consistency. So, to be clear, we are not replacing them. They are amazing tools and will stay for us for a long time. But we need a complementary layer, a distributed data source of a distributed source of truth designed for multi-region data consistency. And that's why my teammate will cover now. We will now switch the speaker. Please bear with us for a moment while we change the equipment.
The speaker will now change. I am Tsuruhara. I will now discuss databases. As the title suggests, I will talk about our decision to adopt Yugabyte DB. As introduced in Javier's part earlier, we are working on the back end of Messenger. We are trying to migrate to a multi-region active-active configuration. I've introduced some of the necessary innovations, but ultimately, the source of truth. A database is necessary. That's the flow. So for this latter half, Yema, our goal is to be able to answer key questions like the ones written here. First, we are trying to adopt a new middleware called Yugabyte DB. But why do we need a new middleware for multi-data center active-active operations? I believe some of you might feel that the topic has shifted a bit, so I'd like to explain that part first. The second point is why Yugabyte DB. Especially in Japan, there are many cases where TIDB is adopted. I will now explain why we did not choose TIDB. So, let's dive into the first point. Why do we need a new database? To reiterate, in the first part of the presentation, I mentioned that our Messenger backend would be moving to an active-active multi-data center configuration. There, we needed a database that would serve as the source of truth. We have shown our approach. So, what exactly is a source of truth, if we try to put it into words? This isn't necessarily how it has to be, but it's what we consider the source of truth. First, from an applications perspective, it actually operates across multiple data centers. We want it to appear as a single database. You want, don't you? Also, we want to be able to read the latest data written in any region from any location. Otherwise, it becomes difficult to develop applications. And of course, even in the event of a major disaster where an entire region goes down, without data loss, we need it to operate, and of course, it must have high availability. Therefore, these things are necessary. So for this whole thing, the existing HBase that we are currently using, we will consider whether this can be achieved effectively. Actually, that's what we thought about at the beginning. I will explain the process. First, even if a region goes down, there should be no data loss. We need to perform cross-region replication. This is self-evident. This is something that absolutely must be done. Normally, if you do this, it will be asynchronous, async commit. If done asynchronously, data loss cannot be completely prevented. What does asynchronous replication mean? After the data is written to the source of truth, this means there's a time lag until that replica is created. Then, when a failure occurs, the data updated or added just before that failure will be lost. That would be a problem. So then, should we replicate synchronously? This presents its own set of problems. So, what does it mean to perform synchronous replication? Writes to both region 1 and region 2 are, this means that once it's committed, it's considered a successful write. What this means, in other words, is that, even if region 1 fails, it will lead to a complete outage, and the same applies if region 2 fails. We wanted to increase availability. We have brought it to the region. If we do this, it will actually lower availability. This would defeat the purpose. So, what should we do? If we think about it naturally, well, when it's operating normally, while replicating with transactional locking. If a failure occurs, stopping replication. Let's provide services with the surviving ones. I think so too. We are talking about active/active. This is where fault detection comes in. This must be done automatically. We want to automate that, especially when there are only two regions. The automatic failure detection here is important. It's quite difficult. That's it. It is said. I think it's difficult because it's called split brain. Because there is a problem. What kind of problem is this? Even though both Region 1 and Region 2 are operating normally, this is a failure, like the network between them being disconnected. This is what happens. They recognize each other as being in a failed state. It assumes it is the surviving primary. If we continue to accept writes from users in that state, then, when replication is resumed, then it becomes unclear which data is real or which is correct, making it difficult for business to continue. It's quite difficult. So, what should we do? Generally, split brain is, as shown in this diagram, by bringing in a third region. This problem can be solved by making it act as an arbitrator. We introduce the third option, which prevents split brains. Even with this, subtle issues still remain. First, even with this configuration, all write traffic will still be because it flows between region 1 and region 2. If the network here goes down, a failover will occur without interruption. When a failure, such as round trip time doubled, occurs, the query latency for all database writes would double. For latency-sensitive services, that's quite a frightening prospect. Therefore, this is also somewhat unacceptable. Also, the failback process after a failover is not trivial. There are still issues. So, what should we do next? Is the question. I imagine it seems quite difficult and complex. Therefore, the answer to the first key question is that's where, well, HBase and its replication. By making good use of it, somehow multi data center, active. Well, I don't think it's impossible. We cannot succeed without creating something quite complex ourselves. This is why we arrived at this conclusion. Existing ones, so to speak, do that a little better. It's about whether it would be better to introduce a watching room. I hope that makes sense to everyone. Now, let's hear about this. I think there might be people wondering, why not just use Cassandra? I won't go into too much detail, but I'll briefly supplement this point. Cassandra, if it performs quorum reads and writes, when the brain is functioning normally, consistent reading and writing are possible. As Cassandra itself states, it provides eventual consistency. There are some corner cases where consistent reads and writes are not always possible, and that's why. How can we use it as a source of truth, which I will introduce later? We believe that a new type of middleware like this would be better. I've been trying hard to explain the issues so far, so what do we do about this? What we want to do is it can withstand region-level failures and high availability. Such replication is necessary. So, what should we do? Actually, in the academic world, in the 90s. So, it's about state-machine replication, is called. There are several algorithms, and it is known that using them allows for highly available and fault-tolerant replication. We believed it would be best to use a database that implements this. So I know keywords like Paxos and Raft. That's right. It's sometimes called that too. Yes. Therefore, databases that actually implement such algorithms are available. There are already several in the world. I've listed about 4 based on my own discretion, and I think many of you might have heard of Cloud Spanner, the one at the top. This is a Google product that implements Paxos. It is a pioneering database in this field. However, for various reasons, it is difficult for us to use it. Since it can only be used by Google Cloud users, we have excluded it from our selection this time. The second one, CockroachDB, I think this is also a very good product, but during our selection process, there was a license change. Since it is no longer open source, we have excluded this from our selection as well. And so, from here, Yugabyte DB and TADB, which are implemented with Raft. Let's compare them. First, I will present 2 rough architectural overviews, but since these are overviews, actually, when abstracted to this extent, both are generally the same. Roughly speaking, there's something like a command system called the control plane. There are 3 or 5 machines. The data plane nodes that it orchestrates. This is a distributed database with many instances. At this level of abstraction, HBase actually has the same structure, but the biggest difference is that this is where the data is replicated. It uses Raft. For distributed processing, it employs a method known as sharding. Many of you are probably familiar with sharding. Logically, a single table. The values of specific columns, which are called primary keys or sharding keys, as a standard and splitting it into smaller units. Here, for convenience, we will call them tablet. Then, for each of these smaller divided tablets, a separate one is used, so that the data processing nodes can handle it. It's a way of distributing Mafka and TDB, Raft, TiDB, and Yugabyte DB. For each tablet, replication is performed using Raft. Here, there are 3 nodes in 3 regions. I will briefly explain how it works based on this premise. If I were to explain Raft in its entirety, we would run out of time, so I will just give you a general idea. Raft forms a group of 3 machines, and first within that group, this means electing a leader node. We will do it. Data read and write operations are basically performed on the leader. Then, when we tell the leader to write the data, the leader first writes to its local disk. The same content will be sent to followers. It will be forwarded for writing. And whichever of the followers, if it can be written to disk, it's considered successful at that point. Is that clear? It's a bit strict, but yes, it's that kind of algorithm. Therefore, in this diagram, if either region 2 or 3 is active, will succeed. Even if one network is slow, if the other can be accessed at normal speed, and the query latency also does not increase. That is to say, then you might think, what happens if the leader dies? In that case, 2 of the surviving followers would be required. It also runs a leader election algorithm. One of them becomes the new leader and continues processing. If you're interested in the details, let's discuss it again later. So far, I've discussed the common architectures of TDB and Yugabyte DB. What I've been discussing so far is to both. This is where it applies. However, there are also quite a few differences in the details. The biggest difference from an application developer's perspective is that TKV is MySQL compatible. Yugabyte DB is compatible with PostgreSQL. So, when migrating existing applications, the difference is quite important. The backend for the messenger is now. We use HBase. Neither is compatible. This is actually not very important to us. The difference in timestamp Oracle allocation methods below it becomes quite important, so I will explain it briefly. So, what exactly is a timestamp Oracle? Both TiDB and Yugabyte DB are databases. Even if many clients access it simultaneously in a consistent order, it is necessary to process them. To achieve this, usually for each transaction, a timestamp or a unique ID is issued to determine the order. However, this is with a distributed database. How it's done is not that obscure. Some of you may have heard of TrueTime in Cloud Spanner. In the case of TDB, it uses something called Timestamp Oracle. This is the only one in the cluster. You would run a process called Timestamp Oracle. It takes sole responsibility for issuing timestamps. This ensures a consistent order. It can be allocated. It's a simple idea, isn't it? In the case of Yugabyte DB, it's not that style. It is called hybrid logical clock. When communicating between nodes is incremented. It's like a combination of a logical clock and a physical clock. Why this works is quite intuitive. I don't think it's possible. The point here is that Yugabyte DB, on the other hand, does not rely on a centralized component like a timestamp oracle. Therefore, we have briefly reviewed the architecture. From here, which one is actually, I would like to introduce the selection process that determines which one to use. We use these three criteria as the three pillars for our selection. The first is whether the feature set implements the functions we need. The second is resiliency. To begin with, what we want to achieve is an improvement in our disaster recovery environment. How quickly we can recover from a failure is a crucial point. The third point is performance. Since this is a database, obviously, the faster it is, the better. Today, I will primarily focus on performance. So, performance factors are service. We have an SLO at this level, so we'll keep that in mind. Benchmark tool, YCSB. Next is a component we call replayer internally. This is a tool that reproduces production environment workloads. We evaluated these two. The test environment is as shown in this diagram. We distributed 9 data plane nodes across 3 data centers. We have configured a cluster of 5 nodes. There are 5 control planes between each network. The round trip time is 30 AMs. We are adjusting it to be that way. So, we tested this in such an environment. Let's quickly look at the performance graphs. This is a production environment. This is the query latency, assuming a certain production environment. So, since it's latency, the lower part of the graph is better. So, if you look at this, the query is very simple, and both TKV and UGBDB are responding in around 2 milliseconds, so there isn't much difference here. Of course, there are patterns where differences emerge. This is an update to the same table, but TKV takes about 35 milliseconds, whereas, even for 1 gigabit, there are cases where a difference of 140 milliseconds can significantly impact performance. So, we drew many graphs like this. We made a comparison. It's obvious if you think about it, but depending on the table schema and the query, the results were completely different, and it was not the case that one was overwhelmingly superior to the other. However, TKV is faster for writes within the scope of our benchmarks. It was more of a tendency, if you will. Hearing that, you might think, then TKV is fine, and cheap. And TDB is, there's one architectural point of concern. That is the timestamp oracle we discussed earlier. TKV uses a timestamp oracle, a process that issues timestamps and exists as a single instance in the cluster. So, in this diagram, the circle on the left, that would be the leader of the control plane node. This means that, as shown in this diagram, depending on the client's location, there will always be patterns where the communication to retrieve that timestamp oracle becomes cross-region. This has an inner round trip time of 30 ms, so there should be a corresponding penalty. This means that query performance should also degrade. When I looked into it, this graph shows the results as predicted. This is the same latency graph as before. So, what about the left side of the vertical line in the middle? This is the performance when the client and the timestamp oracle are in the same data center. At the vertical line, this is the timestamp oracle process, named PD. We move the PD to a remote data center, and the latency is sharply increasing. Cloud spanner. The previous one was the latency for inserts. The same applies to select. 50 ms or so. Latency increases. So, what about reads? Actually, there's a pattern where this doesn't happen. That's interesting, but that's for another occasion. To summarize the performance, though I haven't discussed throughput at all, as a result, there wasn't a significant difference in throughput. Therefore, neither of them has a significant advantage in terms of latency. Yuga Bagate. Light writes can sometimes be quite slow. TKV was from earlier. Regarding timestamp for reads, there are times when it's tough. What should we do in response to this? Oh, before that? Regarding resilience, I will just briefly present the results. Let's keep the results in mind. KO University has experienced various strokes. We measure the time it takes to recover from a crash state, and Yugabyte DB has shown superior results in this regard. In particular, TKV is designed to handle the timestamp oracle process we just discussed. Once it occurs, recovery takes a long time. Given all of this, the question is which one do we choose? The answer is already in the title. Ultimately, our goal was to improve disaster recovery. Next, what are we going to use this for? As introduced in the first half by Havel-san, one application, called the Region Lookup Manager, returns an object in the region where it is primary, which is its mapping. These are quite red-heavy workloads. Therefore, as a result of various comprehensive considerations, we chose Yugabyte DB. We decided to select. Does that make sense? So, as for the 30% that I mentioned, the answer to the key question I first presented, why do we need a new database, is as follows. Existing HBS, or it becomes extremely complex and difficult to implement active-active multi-data center. That's what it comes down to. Why Yugabyte DB was a question often asked, and the comparison was made with TDB. As expected, TDB's timestamp oracle, which is an architectural, the bottleneck was caught, and in the end, we decided on Yugabyte DB. Roughly speaking, that's how it is. Finally, to summarize the entire presentation, what we aim for is, I would like to conclude by introducing the active-active multi-data center configuration. Basically, we use data centers in two regions as active ones, and they receive user requests. So, the stateful part, the database part, we are using Yugabyte DB as the source of truth, while also employing techniques such as the partitioned active-active approach that I discussed in the first half of my presentation. It also uses HBase to handle write-heavy workloads. It is assumed, of course, where caching is needed, we will use a cache. Ensuring that consistency is a difficult problem. We believe that caching can be handled using the techniques introduced in the first half of the presentation. This makes the storage layer complex. Right. To avoid directly implementing such complex logic in the application, we use a storage abstraction layer as an idea. Yes, roughly speaking, we plan to create it. We are aiming for something like this. That concludes my presentation. Thank you for your kind attention. Hello, everyone. My name is Kuboyama from the West Japan Data Center Division. In this session, I'd like to broaden our perspective slightly from the previous themes of software and AI. I will be discussing the facilities that physically and fundamentally support these services that we are working on every day. This is an unremitting effort to reduce air conditioning power consumption at the Chikugo City Data Center. I will discuss our continuous efforts and their current status. This is today's agenda. In the first half, our role as facility engineers in data centers and as a facility engineer, I will discuss the history of our efforts to reduce air conditioning power consumption from the 2000s to the present day. In the latter half, focusing on the latest approach of AI-driven automatic air conditioning control, its mechanisms and effects. Next, I will discuss future prospects. First, there might be many people who are not familiar with us, but we, services for Man Yahoo. In other words, I am a facility engineer who supports facilities. The wide variety of services provided by our company, such as Line and Yahoo, by IT infrastructure, such as servers and networks, is provided. I am in charge of operating the facilities that support this IT infrastructure, such as electricity and air conditioning. Furthermore, facilities such as electricity and air conditioning are, for example, even in the event of a major earthquake or a typhoon. In order not to interrupt services, we operate 24 hours a day, 365 days a year, never stopping this. This is precisely the greatest value we create through facility operations. The Kitakyushu data center, which we operate, boasts an enormous scale. The site area is amounting to stadium after stadium. The facility capacity is an enormous scale of tens of megawatts. Within it, tens of thousands of servers are housed. How to stably operate these enormous facilities, how to operate it efficiently is a very important mission for us. Such enormous data centers consume a vast amount of power. In this way, power consumption, approximately 70% of a data center's power consumption, comes from the IT equipment itself. It is used by the IT equipment itself that provides the services. At that point, regarding air conditioning, is 25%. This is what it's called. It accounts for a large proportion, and this 25% is also a significant percentage. The power consumption of IT expenses is service usage. In other words, it fluctuates depending on the amount of service processing. The servers are generating heat in response. The cooling system, as it's called, addresses the heat generated by IT equipment. We are working to process this appropriately. The power consumption of this air conditioning system is something that we facility engineers, by optimizing operations and equipment usage, this is a large area where we can directly work on efficiency improvement. Here, how we have been working on improving the efficiency of air conditioning power. Let's look back at the history of these challenges. First, the Kitakyushu data center in its earliest days, the 2000s, we were using a typical air-cooled air conditioner called a crack. This is something you use in your homes. This is a standard air conditioner. You can imagine a giant version of this. Following that, with the increasing density of servers, in the 2010s, it can supply chilled water from a central heat source to efficiently cool servers. Central heat source method. What? The cube law and crack. In the 2020s, based on our experience and challenges with the operation of central heat sources, we have shifted to a system that supplies chilled water from distributed heat sources. Also, in line with the expansion of data centers, not only by introducing the latest equipment, we introduced water-cooled air conditioning into an old building from the 2000s, transforming the server room into modern specifications. We are also working on projects. In parallel with the evolution of these air conditioning systems, we have utilized the power of nature. We have continued to tackle the theme of how to address this. From these very first data centers in the 2000s, we are working on server cooling through outside air intake. In the 2010s, furthermore, this outside air intake, we have evolved it. Then, in the 2020s, this is based on the issues derived from our operational experience with outside air intake. We have adopted a pre-free cooling method. Furthermore, currently, we are working on reducing power consumption by combining AI security. This is a cooling system. I will explain the introduction of the guide, pre-free cooling, and refrigerant control later. We have, in response to the demands of IT equipment, evolving air conditioning requirements. Furthermore, in addition to that, the power of nature and by integrating AI-based automatic control. So, we are making progress in our journey toward global data centers. Through the initiatives I've discussed, we have reduced power consumption in this way. As I mentioned earlier, from the 2010s onwards into the 2020s, distributed heat source system. Introducing it temporarily increased power consumption, but by taking on challenges such as implementing pre-free cooling and AI control, we are continuously working to reduce power consumption. Up to this point, I have presented an overall picture of the current situation. Now, I will explain the specific technologies that have supported this challenge. First, this is a direct fresh air intake system that draws cool outside air directly into the server room. Normally, with equipment such as chillers that consume a large amount of electricity, we make chilled water, this light blue arrow. Servers are cooled by sending chilled water. On the other hand, this system also directly incorporates cool outside air, thereby air conditioning system. We are reducing the power burden and power consumption. By the way, this method also has its challenges. Moist air entered through the gaps in the outside air intake vents. The derived power increases. And also, first of all, the outside air is, depending on conditions, such as high humidity or high dust concentration. Considering these operational challenges, we introduced the pre-free cooling method as our next endeavor. In pre-free cooling, at the preceding stage of the chiller that produces chilled water, which I just mentioned, we added cooling tower equipment within the green frame. A cooling tower is equipment that cools water by utilizing the property of water to absorb heat when it evaporates. Thus, by cooling the chilled water in stages, without bringing outside air into the server room, significantly reducing the burden on the chillers. We have been able to consistently reduce the power consumption of our air conditioning systems. Up to this point, I have been introducing the hardware technology. We will apply AI-driven automatic air conditioning control to this. From here, I will introduce our initiatives. This is a schematic diagram of the AI-powered automatic control system. There are two important points here. The first is the placement of these temperature sensors. Here, on these 9 rack surfaces, we have a high-density setup. We have placed temperature sensors. This allows the servers to you can accurately measure the temperature of the intake air. The enormous amount of real-time data obtained from this, centralized in AI. We control the fan speed of the cube. The second important point is precisely this, controlling the fan speed. Everyone. Why not the temperature, but the fan speed? Some people may wonder if it's questionable to focus on that. I will explain that. This involves a physical law called the cube law, as shown in this equation. The power consumption of the air conditioner's fan is as shown in this formula. It is proportional to the cube of the rotational speed n. In other words, this rotational speed n, if you lower it even slightly, the power consumption P dramatically decreases. As shown in this graph, theoretically, by reducing the fan speed by just 25%. By reducing it, the power consumption will be cut by more than half, by as much as 58%. The role of AI is to maximize the utilization of this physical law. So how does AI determine the optimal rotation speed? The key is, with the high-density temperature sensors I just mentioned, it's about finding areas that are being overcooled. Conventional air conditioning control is 1. From the air conditioner, whether to control the blowout temperature to be constant, or based on a table that was decided in advance. The fan speed to control. That approach was common. However, with this method, the actual complex temperature management within the server room, because we are not able to properly anticipate the flow of equipment, even if a hotspot temporarily occurs. To prevent this from happening, excessively low temperatures occurred in areas like this blue section. This overcooled area, this means that electricity is being wasted unnecessarily. So in other words, to prevent this from sensors evenly distributed in small clusters, the entire server room is controlled to maintain an appropriate temperature. The specific algorithm is as follows. AI, which air conditioner, to the temperature of which server rack, how much an impact it has. We continuously learn about the impact of this. First, what happens to the temperature distribution when the fan speed is reduced? We form a hypothesis. We made a hypothesis, and then, based on that, we predict the temperature distribution. We actually adjust the fan speed of the air conditioners. And based on the results of that adjustment, the difference between the prediction and the actual measurement is, and analyze it, relearn the impact. The optimal rotational speed is recalculated. This cycle, by continuing to do this, air conditioners whose demand is excessive, we will reduce the rotation speed of that fan. Through this initiative, we have reduced the power consumption of air conditioning fans by an average of 30%. We achieved the result of saving. The reduction in fan speed itself, as written here. It may seem like a small 5% on average. However, due to the cube law I mentioned earlier, the effect of power reduction will be very significant. Naturally, this is done without creating hotspots in the server room. It remains in an extremely stable state. Additionally, as stated below, some fans saw a reduction in rotation speed by as much as 12%. This means that over half, 56% of the power consumption was reduced in this section. When we introduced AI, we did so knowing the reduction effects it would bring. This time, in an actual operating environment, we were able to verify it. Regarding the optimization of cooling towers, we are talking about equipment. It's not about stopping it, how to rotate it optimally. How? In its original name, we stop the air conditioners with low loads. We tend to run the remaining equipment at high speeds, harnessing the cube law. Operating a larger number of air conditioners uniformly at low rotation speeds results in significantly lower overall power consumption. AI eliminates such human biases and optimize the power consumption of the entire system's air conditioning. We are able to determine the optimal rotational speed to optimize it. The verification results indicate that there is room for further expansion of AI implementation in the future. Finally, here is a look at future prospects. We are currently in the stage of partial optimization, specifically fan speed control. Going forward, we will pursue expanding the scope of AI for overall optimization across the entire data center. In the future, weather forecast data for outside air and server power consumption, we integrated those predictions into the AI system. The ventilation fans, chillers, and cooling towers. Each piece of equipment is a single unit. We aim to operate the data center as an integrated system. Up to this point, we have owned data centers of two companies, and we ourselves, because we operate it, we can explore relentless challenges. I hope this is conveyed in the presentation today. Thank you for your kind attention. I will now present on the topic of Line and Yahoo's Business ID integration. This will be the final session of TechFest 2026. I believe that all of you in the audience will have a social gathering later, but I kindly ask you to hold back your desire to toast for a little while longer and listen for about 10 more minutes. First, a brief self-introduction. My name is Yusuke Tanaka. I joined Line in 2018 and was responsible for developing Line official accounts. And then, in 2021, I transferred to the development of Line Business ID. After the integration of companies and products, I am currently the development lead for Business ID. Today's topic is this. What kind of product is Business ID? How we proceeded with the integration of Business ID, and I'll talk about that reflection. First, regarding Business ID, among those of you participating, some may already be familiar with Business ID, but I would like to briefly explain the product overview. The main topic of this presentation is Line Yahoo Business ID. Those of you who have used the services listed on the right may have seen the screen on the left. This login screen is for Business ID. Business ID is a login platform that supports Line and Yahoo's B2B services. Business ID is used by various services, including Line Official Account, Line and Yahoo Advertising, and Yahoo Shopping. The number of registered accounts exceeds 30 million, and the number of daily active users exceeds 1 million. It is also a very large and important platform that supports Line Yahoo's main B2B services, which are used by over 50 internal services. Next, I will talk about the Business ID integration project. I will discuss the project overview and the innovations within that project. In 2023, Line and Yahoo merged. Line had Line Business ID, and Yahoo Japan had a B2B authentication platform called Yahoo Japan Business ID. Due to the company merger, two business IDs overlapped, which hindered the creation of synergy from the merger. The Business ID integration project aims to resolve this issue. What kind of things come to mind when you hear system integration? The integration we are talking about here has two main meanings. One that is platform integration, which integrates the authentication infrastructure from the perspective of the services used into the new business ID. Another is the account integration feature, which unifies accounts such as Line Business ID and Yahoo Japan Business ID into one. In this presentation, I will mainly discuss the former, platform integration, and at the end, I would like to reflect on the latter. To add to that, in this integration, Line Business ID was chosen as the successor platform. We adopted a method where the authentication function of the Facebook app Business ID is integrated into it. Also, Yahoo Japan Business ID is one function of a larger platform called Business Center. But this time, we proceeded with the project by first narrowing the scope to the authentication function. Now, that concludes the explanation of the product and project. This is the core part of what I'd like to discuss in this session. In this platform integration, instead of making the entire project one large release, we divided the migration into three separate steps. Namely, the migration of authentication functions and the migration of user data in units of services used. Both Line Business ID and Yahoo Japan Business ID are large platforms used by dozens of services, with millions of accounts registered. Because it's used by services that account for Line Yahoo's main revenue, it was very important to integrate it without affecting business services. For this reason, we focused on dividing the release into small steps, making it possible to roll back at each stage. Now let's look at each of these steps one by one. First, the initial step of the integration is the integration of the authentication functions. Yahoo Japan Business ID is a system that allows users to log in with their Yahoo Japan ID. We also implemented the login functionality for Yahoo Japan ID on the new Business ID platform, allowing Yahoo Japan Business ID users to log in as they always have. The new Business ID acts as a single authentication platform from the perspective of the services that use it. However, internally, depending on the account status, there are cases where data from Line Business ID and Yahoo Japan Business ID are referenced respectively. In other words, by having the new Business ID act as a facade, we enabled users, regardless of which system they came from, to log in without significantly altering the implementation on the service side. The second step is switching over to the use of services. There are over 30 services that use Yahoo Japan Business Center. Since each had its own roadmap, it was not realistic to migrate all services at once at the same time. So, we set up a 2-year transition period, allowing each service to migrate its authentication platform at its preferred timing. This design allowed us to proceed with the migration at our convenience without having to wait for user migration. Also, if a problem occurred, we made it possible to roll back simply by reverting the destination. Actually, as we proceeded with the service migration, there were cases where data in an unexpected format came in, and also cases where a rollback became necessary due to IP address restrictions for important customers. However, since we maintained a state where users could log in with either the old or new authentication platforms, we were able to safely roll back in either case and complete the migration after making corrections. This is the current status of the migration. Currently, we are about halfway through the migration period, and while some services are still in the process of being migrated, approximately 80% of the target user base has been migrated. And this is this is the third step, the final step. Thus far, users and services have been safely migrated to the new platform. On the other hand, ultimately, the new Business ID platform must be able to operate independently without relying on Yahoo Japan Business Center. Here too, we avoided large-scale maintenance, such as bulk data migration. Users who no longer used the Business Center had their user data migrated to the new Business ID in sequence. At Yahoo Japan Business Center, service usage requires registration. Therefore, if all services that a user has registered for have been migrated to the new Business ID, that user will no longer need to log in to the Business Center. So, we move data sequentially from users who no longer use the service, transitioning unit by unit rather than in a batch. We designed it to safely eliminate dependencies. By doing this, we aim to safely proceed with the migration on a per-user basis, ultimately reaching a state where the number of Business Center users naturally becomes 0. The third point is a review of the project. This is the most important point I would like you all to remember and take home with you. Looking back, one of the things that went well was migrating from the authentication function. In addition to authentication, Yahoo Japan Business Center has multiple functions, such as company information management, authority management, and payment information management. If we tried to migrate all of them at once, the scope would become too large, and there was a possibility that the start of the integration itself would be delayed. First, by isolating and migrating only the authentication functions, we were able to advance the integration process. Additionally, each service could easily formulate its migration plan, premising that logins would use the new business ID. Secondly, regarding what went well, this was achieved by maintaining the possibility of rollback with each release. No matter how much preparation you do for a system migration, unexpected things are bound to happen. Therefore, it was extremely important to design it in a way that avoided large-scale, simultaneous releases and allowed each release to be rolled back without affecting users. In this project, we maintained a state where users could log in with either the old or new authentication platforms, so we were able to safely roll back in the event of an issue. Finally, I would like to talk about areas for improvement. The point is that account integration may not have been necessary. This project, in addition to platform integration, involves a one-to-one integration of accounts, namely Line Business ID and Yahoo Japan Business ID. We also released the account integration function that merges them at the same time. This was implemented because there was a need to allow users who were using both systems and had two business IDs to log in with a single business ID. However, as a result, this feature might have been unnecessary. The simultaneous release of platform integration and account integration, along with the associated announcements, caused confusion among both internal and external users. There were also problems such as misleading customers about how to use the service, or customers mistakenly linking business IDs together that were not intended to be linked. If we were to design a similar integration next time, instead of simply linking accounts one-to-one, we would like to consider a feature that allows simultaneous login with multiple accounts. To summarize, at LY Corporation, we integrated two B2B authentication platforms following the company merger. Let's review the key takeaways I'd like you to remember. The main point of this design is that we didn't make the integration a single large release. Thank you for listening to my talk. And the migration of user data so that each could be migrated in stages, and maintaining the possibility of rollback at each stage led to a safe migration. We introduced how, even in large-scale environments where maintenance is difficult, integration can be safely advanced by designing for phased migration and rollback capability. Thank you for listening.